Hello there and welcome to Physics with William, where curiosity slows its breathing a little and difficult ideas are allowed to arrive at an unhurried pace. Tonight, or perhaps this morning depending on your corner of the world, we're setting out to consider a question that sounds simple at first and then becomes stranger the longer you sit with it. How strong can any force get? Not how strong a person can become, or how strong a machine can be built, but how strong force itself can be before nature says no further. It is a pleasingly unreasonable question, the sort of question that begins with something ordinary, perhaps a door that sticks a little in its frame, a shopping bag that digs into your fingers, a suitcase that seems to gain weight between the taxi and the front step, and then slowly stretches outward until it reaches stars, black holes, the early universe, and the smallest scales physics has ever seriously tried to describe. We spend much of our lives dealing with force without giving it a proper introduction. We push, we pull, we lift, we press the brake pedal, we turn a key, we stir a cup of tea, and almost never pause to ask what exactly is being transferred from one part of the world to another when something resists and something gives way. Before we go much further, I would love to know where you are listening from and what sort of hour it is there right now. Are you hearing this late at night when the house has finally gone quiet? Or in the early morning before the day has become crowded with tasks? Perhaps you're under a blanket, or perhaps you're at a desk pretending to do something more practical, while secretly keeping company with questions about the upper limits of the universe. Either way, I am glad you are here, and if you find this calm, useful, or simply a pleasant thing to drift off to, I would be very grateful if you gave the video a like and perhaps subscribed. It helps this little space find other people who enjoy science when it is explained without being shouted at. There is already enough shouting in the world. Physics, I think, does not need more volume. It needs a little patience, a steady voice, and the occasional joke when the subject starts taking itself too seriously. Now then, force. It is one of those words that behaves rather differently in daily life than it does in physics. In ordinary conversation, force often means pressure, insistence, maybe even aggression, a forceful personality, a forced smile, force as compulsion. But in physics, the word is more precise and less emotional. A force is something that changes motion. It can start movement, stop it, bend it, slow it, speed it up, or simply keep something from doing what it would otherwise do. That may sound straightforward, but it has remarkable consequences once you begin asking how much of it nature can actually permit. Most of us grow up with a simple intuition about strength. Bigger muscles, bigger engines, bigger explosions, stronger force. That's not wrong exactly, but it is incomplete. A child pushing a toy car, a crane lifting steel, a rocket leaving Earth, and a star collapsing under its own gravity are all examples of forces at work, yet they belong to very different situations and scales. Even the word strong starts to lose its familiar shape when we compare these cases. A person can be strong compared with another person. A machine can be strong compared with another machine. But when we ask how strong any force can get, we're no longer comparing one thing with another. We're asking whether the universe itself has a built-in limit. That is where the topic of tonight begins to show its teeth. Because physics has a curious habit of allowing almost any question to be asked, then answering only some of them in the manner we expected. You might assume, for example, that force can simply keep increasing. Push harder, build bigger, compress more, add more mass, create greater energy, and perhaps there is no upper ceiling at all. Why should there be? Many physical quantities can vary over enormous ranges. Temperatures can rise and fall, distances can shrink and stretch, speeds can increase until they approach that very famous limit set by light. So perhaps force is similar. Perhaps there is no final boundary, only increasingly dramatic circumstances. But modern physics is not always so generous. Again and again, it introduces limits where common sense first imagined none. There is a maximum speed for information to travel. There are smallest meaningful scales at which our current theories stop behaving politely. There are thresholds beyond which matter, no longer stays matter in the everyday sense. There are conditions so extreme that space and time themselves cease to act like the well-behaved background we use for ordinary reasoning, and somewhere in this territory appears a remarkable idea, the idea of Planck force, often described as a kind of ultimate scale for force, a benchmark so large that it sits near the edge of what our present theories can discuss with a straight face. Now, if you are hearing the word Planck and feeling slightly suspicious, that is a sensible reaction. Physics has a tendency to collect these names and present them as though everyone has been casually discussing them over biscuits for years. Planck time, Planck length, Planck mass, Planck temperature. It can start to sound like one very productive scientist decided to claim an entire corner of reality for himself. Max Planck was indeed important, though perhaps even he might be surprised by how often his surname appears in conversations about the foundations of the universe. What matters for us is that the word Planck usually signals a boundary region, a place where gravity, quantum physics, energy, and the structure of space-time all begin crowding into the same room and refusing to wait their turn. That sounds grand, and it is, but the path into it is more grounded than it may first appear. One good way to think about force is to begin not with black holes or the beginning of the cosmos, but with resistance. Force becomes noticeable when something does not simply happen on its own. A book stays on the table because the table pushes upward while gravity pulls downward. A car slows because brakes and friction oppose motion. A tennis ball changes direction because a racket delivers a sharp and very brief push. We live inside layers of forces balancing, competing, cancelling and combining. Most of the time we do not notice because our scale is forgiving. Chairs reliably support us. Floors do not usually collapse. Apples fall at a familiar rate. The world is filled with forces large enough to matter, but small enough to feel normal. Normal, though, is only a local arrangement. It tells us more about our habits than about the full range nature can produce. Consider what happens as we leave human scales behind. Mountains press downward with astonishing weight. Planets squeeze their interiors until rock behaves in ways that would seem bizarre in a kitchen or a garage. White dwarfs pack masses comparable to the Sun into volumes closer to Earth. Neutron stars go further still, crushing matter so severely that atoms, those decent little structures we use to organize chemistry and life, no longer remain intact in any familiar sense. At each step, the forces involved become harder to picture, because our minds are trained on objects we can hold, or at least stand next to. The universe, unfortunately, is under no obligation to remain within the range of our imagination. And even then, gravity is only part of the story. The word force in physics once sat at the centre of a rather elegant list. Gravity, electromagnetism, the strong nuclear interaction, the weak nuclear interaction. 4 basic ways the universe tells things how to behave. That list is still useful, though modern theory often speaks more in terms of fields and interactions than simple pushes and pulls. Electromagnetism is why your fingers do not pass through the table when you tap it. The strong interaction holds atomic nuclei together despite the electrical repulsion between protons. The weak interaction helps govern certain forms of radioactive decay and processes inside stars. Gravity, comparatively feeble at the scale of particles, becomes dominant when enough mass gathers together. So already the question how strong can any force get is not as innocent as it sounded. Which force? In what setting? Measured over what distance? Acting on what kind of thing? Yet Planck force enters the discussion precisely because it tries to name something more universal than a strong magnet or a powerful explosion or a collapsing star. It points toward a scale at which gravity becomes so intense and our familiar categories become so strained that we begin to suspect our current language is no longer the final one. It is not merely a record-breaking force in the way a hurricane wind or a rocket engine might break a previous record. It is a clue about the structure of reality when pushed toward the extreme. There is something quite satisfying about that. Many scientific ideas begin as attempts to explain what has already been measured. Others begin with a mismatch, a stubborn problem, a quantity that keeps appearing in the equations with suspicious importance. Planck scales belong to the second sort. They arise when the constants of nature are combined in a way that suggests a threshold where our best theories of the very large and the very small ought to matter at the same time. Gravity on one side, quantum mechanics on the other, general relativity with its smooth geometric view of space-time, quantum theory with its restless discrete behaviour and probabilities. Usually these theories operate in rather different neighbourhoods. One speaks comfortably about planets, stars, galaxies and black holes. The other speaks with great success about particles, atoms, radiation, and the strange rules that govern tiny systems. But there are rare and extreme circumstances where both must be invited to the same conversation. The earliest universe is one, the deep interior of black holes may be another, and when they meet, nobody expects the discussion to stay tidy. That is why asking about the maximum possible force is not just a search for a giant number. It is a way of probing where our current map becomes unreliable. If there is such a limit, it may tell us something profound about how gravity constrains energy and motion. If there is not, that matters too, because it tells us the universe is more open-ended than some physicists have suspected. Either way, the question acts like a lever. Pull on it gently enough, and a great many other topics begin to move. Why do black holes have horizons? What happens when matter is compressed beyond every ordinary description? Are there quantities nature keeps finite by design? Or are those apparent limits merely features of our incomplete theories? When space-time becomes violently curved, is force still even the right language? There is also a more human side to the question which I think is worth keeping in view. We like limits, even when we claim to dislike them. We ask what is the coldest possible temperature, the fastest possible speed, the brightest possible object, the heaviest stable element. Part of that is practical curiosity. Part of it is emotional. Limits make the universe feel shaped rather than arbitrary. They suggest there is an order to things, even in regions we will never visit. To say there might be a maximum force is to say the cosmos is not just a wild collection of events, but a place where some boundaries are written deep into the rules. Of course, physics has played tricks on us before. Things once thought impossible later became routine. Other things once thought obvious turned out to be merely local habits of our experience. So we should not approach Planck force as a final slogan or a magical capstone placed on top of all physical knowledge. It is better to treat it as a serious proposal about the scale at which the familiar ideas of force, gravity, size and energy begin to crowd against the limits of our current understanding. That way we can remain honest about what the concept clarifies, honest about what is still debated, and honest about how much of the subject lives at the edge of tested physics rather than comfortably inside it. Even so, the edge is often where the most interesting questions live. It is where ordinary language starts to wobble and scientific language has to work harder. It is where one can no longer simply say stronger means more and leave it there. Stronger than what? Applied where? Over what interval? With what consequence for the thing being acted upon, and for space-time itself? A gentle push on a door and the inward crush of a collapsing star both count as force in some sense, but they belong to realities so different that using the same word for both feels almost mischievous. Planck force asks us to keep that discomfort rather than smoothing it over too quickly, and perhaps that is an appropriate mood for the start of this journey. Not confusion exactly, but a willingness to let the question stay large for a while, before we force it into a neat box. Because the cleanest scientific explanations often come only after we've noticed how messy our first intuitions were. We think force means effort, then discover it means change of motion. We think strength means muscle, then discover stars and fields do most of the impressive work. We think bigger always means stronger, then discover scale can transform the rules entirely. Somewhere ahead lies the strange claim that there may be a natural benchmark for the most intense force nature can sustain. A benchmark connected not to steel or engines or even ordinary matter, but to the deep structure of space-time itself. To reach that point sensibly, it helps to begin lower down and make sure the ground under our feet is firm. What exactly do physicists mean by force when they strip away metaphor? And why has that simple-sounding idea proved so useful for describing everything from a falling apple to the collapse of a star? Force is one of those words that seems perfectly familiar until you ask it to sit still for a proper definition. In daily life, we use it with great confidence. We force a drawer shut. We force a laugh when we're tired. We speak of forceful winds, brute force, armed forces, market forces, even the force of habit, which may be the most persuasive one of all. The word arrives already wearing several coats at once. It suggests pressure, effort, compulsion, energy, strength, and sometimes a certain lack of subtlety. So when physics borrows the same word and insists that it means something precise, there is bound to be a little confusion. The useful thing, though, is that our everyday instincts are not entirely wrong. They are just too broad. When you push a chair across the floor, you really are doing something close to what physics means by force. When you pull open a heavy door, lift a bag of groceries, or press your foot against a pedal, you're participating in the same basic idea. A force in physics is not just effort in the emotional sense or pressure in the social sense. It is something that changes the motion of an object or tries to. That last part matters. Sometimes the change happens clearly and immediately. You kick a ball and off it goes. Sometimes the attempt is opposed by something else. You push against a wall and, to your disappointment and the wall's quiet satisfaction, nothing visibly moves. But a force is there all the same. This is where the subject starts becoming more interesting than the word suggests. Because motion is a slippery thing until you pin down what counts as a change. If a book rests on a table, it looks as though nothing is happening. The book is still. The table is still. The room is still unless someone has left the window open. Yet even in this quiet arrangement, forces are at work. Gravity is pulling the book downward. The table is pushing upward. Those two influences balance each other so the book remains at rest. Rest, in this sense, is not the absence of force. It is the result of forces that cancel out. That point is worth lingering over because it corrects one of the most common early misunderstandings about motion. Many people begin with the feeling that if something is moving, there must be a force keeping it moving. That seems reasonable. A bicycle slows down when you stop pedaling. A shopping trolley rolls only so far before it loses interest. A football kicked across grass eventually gives up and lies there. Everyday life trains us to associate motion with ongoing effort because friction and air resistance are constantly interfering. But if you remove those complications, the picture changes. An object does not need a force to keep moving steadily in a straight line. What it needs a force for is to change that state, to speed it up, slow it down, turn it, or stop it. Constant motion, oddly enough, is the lazy option. Change is what requires intervention. That insight was one of the great clarifications of early modern physics. It helped separate what the world seems like from what it is doing underneath the distractions of everyday experience. A puck on smooth ice glides much farther than a book shoved across a carpet because there is less opposition, not because the puck has been blessed with superior motivation. Spacecraft once launched and guided can coast for astonishing distances because space offers very little friction. The old intuition that motion must be continually fed by force turns out to be more about living on a dusty, drag-filled planet than about the rules of nature themselves. So when physicists say force changes motion, they mean something precise. A force can alter speed. It can alter direction. It can do both at once. If a car accelerates down a straight road, force is involved. If a planet follows a curved path around a star, force is involved there too, even though the planet may be moving at a nearly steady speed. Turning counts as a change in motion because direction is part of motion, not merely decoration. That is why circular motion is never truly passive. Something must be continually guiding it away from straight-line travel. Swing a stone on a string, and your hand feels that guidance as tension. Watch the moon circle Earth, and gravity is doing the job from a distance. Distance is another place where intuition needs some adjustment. Some forces involve direct contact. You push a cart. The cart pushes back on your hands. A floor supports your weight through the electromagnetic interactions between the atoms in your shoes and the atoms in the surface beneath you. A bat strikes a ball. A hammer meets a nail. These all feel satisfyingly concrete. But not every force arrives by touch. Gravity acts across space. A magnet can tug a paperclip without making contact. An electric charge can influence another charge from afar. This can feel slightly mysterious at first, as though nature were cheating. We are comfortable with one thing shoving another thing. We are a little less comfortable with invisible influence stretching across emptiness. Physics eventually made peace with this by replacing the simple picture of action at a distance with the richer idea of fields. Instead of imagining one object somehow reaching across space to grab another, we describe space around an object as being altered in a structured way. A massive body shapes the gravitational field around it. A charged particle shapes the electric field around it. Another object entering that field responds accordingly. This does not remove all mystery, but it organizes it much more effectively. The world becomes less a collection of isolated lumps colliding like billiard balls, and more a continuous web of influences spread through space. That shift matters because when people first hear the word force, they often imagine muscular pushing. Physics allows for that, but does not stop there. It includes the quiet support of a chair under a seated person, the pull of Earth on the oceans, the binding of particles inside an atomic nucleus, and the guidance of light and matter by invisible fields. The word covers a larger territory than common speech usually grants it. In fact, one reason force remains so useful is precisely because it lets us describe wildly different situations with a shared conceptual tool. The same basic language that helps explain why a mug falls off a table also helps explain why stars hold together, why planets orbit, and why atoms do not simply fall apart. Still, there is a danger in leaning too hard on the word. It can make all influences sound more similar than they really are. In school-level physics, force is often presented as the central actor, because it gives a clean and practical way to relate motion to causes. That is excellent for many purposes. Engineers rely on it. Pilots rely on it. Builders, machinists, athletes, and anyone who has ever tried to stack boxes in a moving van rely on it whether they use the vocabulary or not. But deeper theories sometimes speak more naturally in terms of energy, momentum, fields, and interactions. Force remains useful, but it is not always the final layer of description. It is a bit like discussing music in terms of notes and rhythm. That can take you very far. Yet sometimes harmony, resonance, or the physical vibration of air tells a fuller story. Even so, the ordinary idea of force deserves careful attention because it teaches something fundamental about how the world resists simplicity. Nothing moves in complete isolation. Every motion is a negotiation. A runner pushes backward against the ground and the ground pushes forward. A bird beats the air downward and the air responds by helping hold the bird aloft. A swimmer presses water behind and is carried ahead. In each case, movement is not the triumph of one object over passive emptiness. It is a relationship. Force tells us that motion is not merely about what something wants to do, if objects can be said to want anything. It is about what the surrounding world allows, opposes, redirects, or amplifies. This relational quality becomes even clearer when we consider mass. Not everything responds to force in the same way. Push an empty shopping cart and it darts away with almost embarrassing eagerness. Push a loaded one and suddenly you're in negotiation with a very different level of resistance. The distinction is not just weight in the ordinary sense, it is inertia, the tendency of matter to resist changes in motion. Mass is, among other things, a measure of how stubborn an object is when you try to alter its state. More mass means more reluctance. The same shove that sends a ball skittering across the floor will barely disturb a sofa unless you're having an unusually productive afternoon. This is one of the elegant features of the concept. Force by itself is not enough to predict what will happen. You must know what kind of object is being acted upon and how much inertia it has. A child and a train do not respond in the same way to the same influence, which is fortunate for trains and mostly fortunate for children. The world is full of such mismatches. Wind bends grass but only nudges a building. Sunlight warms a stone but can drive a delicate sail. A small magnetic field might barely affect one material while dramatically shaping another. Force always belongs to a situation. It is never just a number floating free of context. There is also the matter of duration. A force applied gently over a long time can produce a very different outcome from a stronger force delivered in an instant. Push a swing with small repeated nudges and you can gradually build a substantial motion. Strike something sharply and the effect is more abrupt. This is why a catcher's glove is thick and why crumple zones in cars are designed to give during impact. Spreading change over a little more time can make a severe encounter more manageable. Once again, force is not just about raw strength. It is about how change is delivered, how quickly, how steadily, and through what material. Materials matter enormously because they determine how force travels through matter and how matter responds when pushed too far. Press gently on a cushion and it yields. Press on stone and the stone gives much less, though not infinitely less. Pull on a rubber band and it stretches. Pull on glass and it resists until quite suddenly it does not. All matter has ways of storing, redistributing, and eventually surrendering to force. Buildings sway in wind, bridges flex under load, bones bear weight with quiet competence until a threshold is crossed. The study of such responses is part of what makes mechanics feel less like abstract theory and more like a conversation with the physical world. Matter is not merely there, it has character. By this point, the word force has expanded well beyond brute pushing. It has come to include balance, resistance, response, relationship, timing, and structure. Yet there is still another refinement waiting. In modern physics, especially at deeper levels, forces are often understood not as independent mysterious pushes, but as manifestations of interactions carried by fields and particles. Electromagnetism, for example, accounts for a vast amount of what we experience as ordinary contact. When you sit in a chair, you do not actually sink through it, because the atoms in your body and the atoms in the chair do not simply interpenetrate. Their charged components resist one another through electromagnetic interactions. So the very solidity of the world, which feels so obvious that we rarely question it, is already a subtle achievement of invisible forces playing by microscopic rules. Gravity, too, is stranger than it first appears. At human scale, it feels familiar enough. Things fall, we stay on the ground, rain comes down instead of wandering off sideways. But according to general relativity, gravity is not quite a force in the old sense at all. It is the effect of curved space-time guiding motion. Objects follow the geometry available to them. That does not make gravity less real. It makes it conceptually more interesting. The falling apple and the orbiting planet are not being yanked by an invisible rope in the crude sense. They are moving according to the structure of space-time around mass and energy. Yet in many practical settings, speaking of gravity as a force remains perfectly effective. Physics often keeps older language when the older language still works, even if the deeper interpretation has changed. This flexibility is one reason the subject can feel both satisfying and slightly treacherous. Ask what force means, and you get a clean answer. Force changes motion. Stay with the subject longer and the answer grows branches. Force can be balanced, hidden inside equilibrium. It can arrive through contact or through fields. It can act continuously or briefly. It can be described well in classical terms and then reinterpreted in deeper theories. It can seem central in one context and secondary in another. None of this makes the concept weak. Quite the opposite. It shows how much the concept has had to carry, and it also prepares us for a more serious question. Once you understand force as the capacity to alter motion, and once you see that the world is built from countless interacting forces that balance, redirect, and sometimes overwhelm one another, the next natural thought is about scale. How large can such influence become? At what point does ordinary language stop being useful? We can imagine stronger and stronger pushes. We can build more powerful engines. We can observe more violent collisions, but nature is not obliged to let that ladder continue without end. Perhaps there are conditions under which matter gives way before force can increase further. Perhaps spacetime itself imposes a ceiling. Perhaps the deepest rules of the universe place a bound on how intense any interaction can become before our current categories dissolve. That is not the sort of question that would have occurred to most people while pushing a chair across a kitchen floor, but it is built from the same ingredients. Every grand physical mystery usually begins in some modest observation if you trace it back far enough. Why did the chair move? Why did the ball stop? Why did the apple fall? Why did the planet not fly away? Why does matter resist compression? Why do objects keep their motion unless something interferes? One question hands the next question forward, and before long you are standing at the edge of black holes, collapsed stars, and the possibility that force itself may have an upper limit written into the architecture of reality. So when we ask what we really mean by force, the answer is not just a dictionary correction. We mean the world refusing to remain unchanged. We mean motion being guided away from its previous course. We mean matter responding according to its inertia, its structure, and the fields around it. We mean balance and imbalance, contact and distance, the seen and the unseen. We mean one of the simplest ideas in physics and one of the most far-reaching. And now that the idea has a clearer shape, we can begin following it outward from the familiar scenes of ordinary life into the much larger story it belongs to, from the old image of falling apples to the violent and astonishing places where nature tests its own limits. It is one thing to notice that an apple falls. It is another to realize that the same rule pulling that apple toward the ground also helps hold the moon in its path and governs the motion of planets, comets, and stars. That step from the ordinary to the universal is one of the great expansions in the history of thought. It begins with familiar scenes, fruit dropping from a tree, stones thrown upward and then returning with disappointing loyalty to earth, cartwheels slowing in mud, doors resisting a shove. It ends, or rather continues, in places so extreme that matter is squeezed past every comfortable description we once gave it. White dwarfs, neutron stars, black holes, stellar collisions, the collapse and reconstruction of entire suns. And through all of it runs the same underlying question. What is force doing here, and how far can its reach extend? The falling apple has become almost too famous for its own good. It appears in popular retelling so often that one could be forgiven for imagining Isaac Newton spent most of his life sitting under fruit trees, waiting to be struck into genius. The truth is both less theatrical and more interesting. Whether or not any apple ever landed near him at the decisive moment matters less than the insight associated with the story. Newton recognized that the motions we observe on Earth and the motions we observe in the heavens need not belong to separate categories. Before that, there had been a long habit of thinking of celestial motion as something cleaner, more perfect, and perhaps governed by principles quite unlike the grubby mechanics of daily life. The heavens seemed to move with regularity and grace. Apples, by contrast, simply fell on people and spoiled the picnic. What Newton supplied was not merely a better answer about falling bodies, but a daring unification. The same gravity that tugs an apple downward could be the reason the moon continually bends around Earth instead of flying off into the dark. In that idea, a force that once seemed local and familiar suddenly became cosmic. The Earth was no longer a separate stage with its own private rules. It was one participant in a larger orderly system. That recognition changed everything because it implied that the universe was not stitched together from different kinds of reality for different places. It was one place governed by the same logic from garden to planet to star. There is something quietly thrilling about that kind of simplification. Physics often progresses not by making the universe more complicated, but by discovering that many apparently different things are the same thing wearing different coats. A falling stone and an orbiting moon look nothing alike at first glance. One goes down, the other goes around. Yet the difference is less about the nature of the force than about the circumstances. The stone has too little sideways motion to miss the Earth. The moon has enough sideways motion that as it falls, it also moves forward, and the curved surface of Earth drops away beneath it at just the right rate. The moon is, in a sense, always falling and never quite arriving. This is a wonderfully unsettling thought. It takes something as familiar as gravity and reveals it not merely as a downward pull but as the architect of celestial motion. Once that door opened, it became possible to think of the universe as a connected mechanical whole. Planets could be treated not as divine lamps wandering through the sky, but as bodies subject to measurable forces. Tides could be linked to the gravitational influence of the moon. Comets could return according to predictable paths, instead of serving only as ominous announcements that kings should perhaps prepare for bad news. The language of force turned observation into calculation. It made the cosmos less like a pageant, and more like a system. This did not make the universe smaller in wonder. If anything, it made it more astonishing. A rule simple enough to explain why your dropped cup falls from the table could also describe the motion of the worlds. The old split between earthly and heavenly events began to dissolve. It became possible to believe that if the same force acts everywhere, then the distant stars are not beyond understanding, remote certainly, dangerous in many cases, inconveniently hot, but not incomprehensible. That confidence deepened over time as physics learned to describe more and more kinds of force. Gravity explained the large-scale choreography of the cosmos, but it was not the whole story. Matter itself had internal structure: heat, light, electricity, magnetism, pressure, and chemical behavior all had to be brought into the same growing framework of explanation. The old image of force as simply pushing and pulling acquired layers. The pressure inside a steam engine, the charge in a thunderstorm, the magnetic field guiding a compass needle, the structural strength of a bridge. All of these invited more precise thinking about how matter transmits influence and responds to it. By the time the 19th century gave way to the 20th, the universe had become more crowded and more disciplined at once. Crowded because science had discovered whole new classes of phenomena. Disciplined because these phenomena increasingly turned out to obey general laws. The sun, for instance, could no longer be treated as a permanent lantern hung in the sky. It had to be understood as a physical object with a history, an interior, and a source of energy. That question, how stars shine for so long, turned out to be one of the crucial steps from the old mechanics of falling apples to the far more intense realm of stellar forces. At first, the sun presented a genuine problem. If it were powered by ordinary burning, it could not shine for anything like the time geology and biology seem to require. A cosmic bonfire runs out too quickly. Something deeper had to be happening. The answer emerged only when physics learned enough about atoms and the nucleus to understand that stars are not chemical fires at all. They are engines of nuclear fusion. In their cores, matter is pressed and heated so severely that nuclei can combine, releasing tremendous amounts of energy. This was a revolutionary shift in our sense of scale. The forces inside stars were not merely larger versions of the forces in furnaces or fireplaces. They belonged to a different domain altogether. And here the story becomes especially relevant to our larger question. A star exists because forces are in competition. Gravity pulls inward, trying to compress the star. Pressure generated by the hot interior pushes outward. As long as these influences remain in balance, the star lives in a kind of long-maintained truce. It glows because the inward squeeze creates the conditions for fusion, and fusion in turn creates energy that helps resist further collapse. A star, then, is not just a ball of gas. It is an active negotiation between opposing tendencies. Gravity wants more compression. The interior fights back. The result is radiance. This alone is a magnificent expansion of the concept of force. The falling apple tells you gravity acts. The shining star tells you gravity acts so persistently and on such scales that it can build conditions fierce enough to transform matter at the nuclear level. Force is no longer just the reason things drop. It becomes the reason whole stars sustain themselves for millions or billions of years. But stars do not remain in equilibrium forever. Their lives are long, but they are not endless. Over time, the fuel in their cores changes, the balance shifts. What happens next depends on mass, and mass in astrophysics is one of those blunt facts that determines character more efficiently than any horoscope ever has. Smaller stars age more quietly. Larger stars live faster and die harder. Once the core can no longer support the weight of the outer layers through the same fusion processes, gravity regains the upper hand. Then the inward pull that once enabled the star to shine becomes the force that drives its collapse. This is where the path from apples to stars becomes far more dramatic. A star in collapse does not merely shrink politely. The process can become violent, unstable, and transformative. Outer layers may be blown off. Cores may be crushed. Entire new forms of matter may appear. Depending on the circumstances, the remains may settle into a white dwarf, a neutron star, or continue beyond those into black hole formation. These are not just different size leftovers. They are different answers to the question of what matter does when pushed beyond ordinary limits. A white dwarf is already a deeply strange thing. Imagine a mass comparable to that of the Sun packed into a volume closer to that of Earth. Matter there is supported not by ordinary gas pressure, but by quantum mechanical effects related to the unwillingness of electrons to be squeezed into the same states. In other words, the star resists gravity not with heat in the everyday sense, but with a distinctly quantum form of pressure. Even at this level, the concept of force is changing texture. It is no longer enough to speak vaguely of compression and support. One must account for the quantum behavior of matter under extreme density. Push further, and the universe becomes stranger still. A neutron star forms when gravity wins past the white dwarf stage. Electrons and protons are driven together, creating neutrons in large numbers, and the result is an object of extraordinary density. A spoonful of neutron star material, if one could somehow borrow it without everything going badly wrong, would weigh far beyond anything our daily intuitions are built to handle. Here matter is held up by neutron degeneracy pressure, and by the strong interaction between particles packed into conditions that are difficult to reproduce and only partially understood. The surface gravity is immense. The magnetic fields can be ferocious. The star may rotate with astonishing speed, flashing beams of radiation across space like a lighthouse that has entirely given up on moderation. What matters for our discussion is that this is force made visible in forms no orchard could prepare you for. Gravity has compressed a stellar core until the distinction between familiar solid, liquid, and gas has long since ceased to be useful. Matter has entered a regime where atomic structure is overwhelmed, where pressure arises from quantum principles, and where the scale of inward squeeze begins to hint at the kind of extremes that make physicists start reaching for Planck units later in the story. The road there does not begin with abstractions. It begins with gravity being allowed to continue its work almost without mercy. And then there are black holes, where our language becomes even more cautious. In the old Newtonian sense, one might be tempted to say, gravity simply becomes infinitely strong. But general relativity asks for a more careful description. Gravity is no longer treated as a force acting through space in the usual way, but as the curvature of space-time itself. A black hole is not a cosmic vacuum cleaner with rude manners, though popular writing often introduces it that way. It is a region where mass and energy have curved space-time so severely that there exists a boundary beyond which escape is no longer possible. Light itself cannot get out once it has crossed the event horizon. That fact alone should tell us we are very far from the world of falling fruit and thrown stones. Yet continuity remains. The apple and the black hole belong to the same broad story. Gravity is present in both. The difference lies in strength, geometry, scale, and consequence. The apple falls a short distance through weakly curved space-time on a planet with modest gravity by cosmic standards. A black hole represents gravity driven into a regime where the structure of space-time becomes central to the description. If physics teaches humility anywhere, it is here. A force that appears familiar at one scale can become conceptually transformative at another. Still, stars do not merely collapse in isolation. Some of the most violent events in the universe occur when compact objects interact. Binary systems, where two stars or stellar remnants orbit each other, can become laboratories of astonishing intensity. Matter may be pulled from one object to another, orbits may decay, magnetic fields may tangle, tidal forces may rip material into streaming spirals. If two neutron stars merge, the collision releases energy on a scale so vast that for a brief period it can outshine whole galaxies in certain wavelengths. Such events also produce gravitational waves, ripples in space-time itself, which human instruments have now detected. That sentence alone would have sounded unreasonable not very long ago. We now observe not just light from the heavens, but the slight shaking of space-time caused by cataclysmic events far away. There is something appropriate in that. As our understanding of force expanded, our means of observation expanded with it. We no longer rely only on visible light and patient sketches of the sky. We listen to the universe through radio waves, X-rays, gamma rays, neutrinos, and gravitational waves. Each new window reveals that the cosmos is more active, more extreme, and more mechanically rich than earlier ages imagined. Colliding stars, collapsing cores, erupting jets, warped space-time. These are not poetic exaggerations. They are physical events governed by rules that connect back, however distantly, to the same logic that once explained why objects fall. And yet the farther outward we go, the more the old intuition of force as a simple push or pull begins to feel incomplete. Stellar interiors require nuclear physics. Compact objects require quantum pressure and relativity. Mergers require highly dynamic space-time. In some regions of the universe, force is not best imagined as a shove, but as a balance, a field, a curvature, a density-driven threshold, or a geometry shaping what counts as motion at all. This is why the history from Newton onward is not merely the accumulation of bigger examples. It is a change in what the word means as the contexts become more severe. It is also a lesson in scale. Human beings are inclined to think of size and power in the same breath. Bigger machine, bigger force, bigger explosion, bigger consequence. That works up to a point, but astrophysics complicates the picture. A white dwarf is small compared with an ordinary star, yet far denser. A neutron star is smaller still, yet more extreme. A black hole may be smaller than the star that formed it, yet its grip on nearby space-time is far more intense. Compression changes the terms of the discussion. It is not just quantity of matter that matters, but how tightly it is packed, and what that packing does to the laws governing the system. Force becomes not merely a matter of amount, but of concentration, confinement, and the structures that emerge under pressure. This is especially important when thinking ahead to the possibility of a maximum force. The universe does not simply allow us to scale up ordinary situations indefinitely. Matter changes phase. Atoms break down. Nuclei are transformed. Quantum effects become unavoidable. Relativity enters. Horizons form. In other words, nature keeps changing the rules of the game as the stakes rise. That is why the journey from apples to stars is not just a travelogue of increasing spectacle. It is evidence that the concept of force must be handled differently as we move toward extreme conditions. The old language survives, but it has to be sharpened and sometimes reinterpreted. There is another reason this historical arc matters. It reminds us that the most radical ideas in physics often begin in the act of taking something ordinary very seriously. Apples fall all the time. Most people are content to dodge them or eat them. Newton treated the fall as a clue. In much the same way, later physicists treated sunlight, spectral lines, radioactivity, orbital shifts, and starlight as clues. The universe rarely announces its deepest truths in a tone of voice we cannot miss. It tends instead to repeat small facts until someone notices that their implications are enormous. So when we look at colliding stars, at supernova remnants, at neutron star mergers, at black holes feeding on disks of infalling matter, we are not looking at a separate and extravagant universe disconnected from our own. We are looking at our own laws under stress. The forces are stronger, the consequences harsher, the conditions less forgiving, but the continuity remains. That continuity is what makes the subject so compelling. The cosmos is not stitched together from unrelated surprises. It is one place, and its most violent episodes are elaborations of the same principles that first reveal themselves in the modest motions of the everyday world. By the same token, the farther we follow those principles, the more we are led toward hidden scales and deeper limits. Apples and planets gave us gravity as a universal rule. Stars taught us that gravity can compress matter into regimes where nuclear and quantum physics are unavoidable. Compact remnants showed that pressure itself can come from microscopic principles entirely absent from everyday experience. Black holes demonstrated that spacetime is not just a stage, but part of the action. And once spacetime itself joins the cast, the idea of asking how strong force can become begins to sound less like idle curiosity and more like an unavoidable next step. Because after the orchard, after the equations of motion, after the rise of stellar physics and the discovery of collapsed stars, one starts to suspect that nature may have deeper scales built into it, scales at which our usual categories of size, duration, mass, and force stop being separate practical tools and begin clustering into something more fundamental. That suspicion leads us away from individual stars and toward the strange territory where gravity, quantum mechanics, and the structure of space-time must all be considered together, and where the name Planck begins to enter the conversation with increasing seriousness. By the time physics had followed gravity from falling apples to stars, and from stars to collapsed remnants and black holes, a new problem began waiting quietly in the background. The old descriptions were not exactly failing, but they were no longer enough on their own. General relativity gave a powerful account of gravity, space-time, and the behavior of massive bodies. Quantum mechanics gave an equally powerful account of atoms, particles, radiation, and the small-scale structure of matter. For most of the universe, these two great frameworks can go about their business in different neighborhoods. Relativity handles the very large. Quantum theory handles the very small. Each is astonishingly successful where it is meant to be used. The trouble begins when nature seems to demand both at once. That demand does not show up in ordinary life. You do not need quantum gravity to butter toast or catch a bus. You do not need it to predict the motion of a bicycle or the orbit of the moon. Even stars for much of their lives can be described very well without forcing the deepest levels of relativity and quantum theory into direct confrontation. But when you start asking about the earliest moments of the universe, or the deepest interior of a black hole, or the ultimate limits of compression, density, and force, then the separation stops being comfortable. Suddenly the large and the small are in the same room together, and neither theory is entirely willing to give up its authority. This is where the Planck scale enters the story. It is not a place in the way Paris is a place, nor is it a solid object waiting at the bottom of matter like a tiny brick with Max Planck's name stamped on the side. It is better understood as a family of natural scales that emerge when we combine the key constants governing gravity, quantum mechanics, and relativity. In more human terms, it is a warning sign. It tells us that if we push far enough into extreme conditions, the ordinary language of space, time, mass, energy, and force may no longer behave in the smooth and separate ways we're used to. The Planck scale marks the region where our best theories begin stepping on each other's shoes. There is something deeply attractive about this idea. Physics has long relied on the hope that nature has preferred scales built into it. Certain quantities seem to matter not because humans invented them, but because the universe itself does not care about our meters, seconds, or kilograms. We chose those for practical reasons. The universe did not consult us, but sometimes, by combining the constants of nature in the right way, physicists find scales that seem less human and more fundamental, scales that appear to be written into reality itself. Max Planck was one of the first to notice this kind of possibility clearly, which is why his name ended up attached to an entire district of the cosmic map. Planck himself was not originally trying to invent the smallest stage of existence. He was working on the problem of thermal radiation at the end of the 19th century, in a period when physics was beginning to discover that the microscopic world was not going to behave with the same neat continuity people had assumed. His work helped launch quantum theory by suggesting that energy exchange was not perfectly smooth, but came in discrete chunks. That alone would have secured his place in history. But the scales that now bear his name came from another insight as well. If you combine the constants associated with gravity, quantum behavior, and the speed of light, you can construct units of length, time, mass, and other quantities that do not depend on any local custom. In that sense, they are natural units, drawn from the architecture of the universe, rather than from the length of a king's arm or the timing of the Earth's rotation. The Planck length is often introduced first because it is so startlingly small that it immediately makes the imagination cough politely and ask to sit down. It is not merely small in the way a cell is small or even in the way an atom is small, it is incomprehensibly smaller than that. If an atom already feels far beyond direct everyday intuition, the Planck length is smaller than an atom by such an enormous margin that common visual metaphors begin to wear out. We can say it is tiny, but tiny is a village word trying to describe a galaxy. The point is not just that it is very small. The point is that at such a scale, the usual picture of space as a smooth stage may stop being trustworthy. That last claim needs care because popular science has sometimes encouraged the impression that the Planck length is definitely the smallest possible piece of space, as though the universe were made of a little cubic tiles, and this were the edge length of the tile. That is more certain than physics currently allows. The honest position is subtler. The Planck length marks the scale at which our current theories suggest spacetime may no longer be describable as a smooth classical continuum. It is a threshold of expected trouble, not a photographed grain of reality. Some theories of quantum gravity do suggest that space may have a discrete or quantized structure in some sense. Others do not picture it so straightforwardly. The Planck length is therefore best treated as a sign that our present description breaks down, not as a fully mapped floorboard beneath all existence. The same is true of Planck time. This is the timescale associated with the Planck length and the speed of light, and it is unimaginably brief. If a second already contains more fine structure than the human mind can feel directly, Planck time is so much shorter that talking about before and after begins to sound almost mischievous. It is often described as the shortest meaningful interval of time, but again, the most careful phrasing is that it is the scale below which our current concepts of time may no longer make operational sense in the usual way. If you ask what happened before one Planck time after the beginning of the universe, modern physics becomes cautious. Not necessarily because nothing happened, but because the tools we have are no longer reliable enough to answer with confidence. This is what makes the Planck scale feel less like a measurement and more like a frontier. It tells us where our conceptual machinery starts rattling. We can extrapolate our theories towards such regimes, and the numbers we obtain are informative. But the closer we get, the more we suspect that space-time itself may fluctuate, become foamy, or require a description unlike anything in ordinary relativity. That word, foamy, has become popular because it captures the loss of smoothness without pretending to explain it too neatly. Space at everyday scales seems calm and continuous, much as the surface of a sea may look smooth from far away. But viewed closely enough, perhaps the structure is restless, granular in some deeper sense, or governed by processes that make the old image of a serene geometric stage inadequate. The Planck mass often surprises people, because unlike the Planck length and Planck time, which are absurdly small, the Planck mass is not vanishingly tiny by ordinary particle physics standards. It is still small by everyday standards, of course, but in the world of elementary particles it is unexpectedly large. That matters because it hints at the bizarre crossing point where quantum ideas and gravitational ideas begin to matter together. A particle at the Planck mass would not be just another small object. It would sit near a region where our separate ways of talking about particles and space-time geometry start interfering with each other. The Planck scale is full of these little conceptual ambushes. The small becomes large, the simple becomes unstable, and familiar categories stop minding their manners. One reason physicists care so much about these scales is that they point toward a deep incompleteness in our present understanding. General relativity is a classical theory. It treats space-time as smooth and continuous, beautifully curved by matter and energy. Quantum mechanics, by contrast, insist that the microscopic world has a different character, one in which uncertainty, discrete exchanges and probabilistic structure are unavoidable. Each theory is magnificent in its proper range. But a black hole singularity, or the earliest instant of the Big Bang, seems to be asking for a theory in which gravity itself is somehow quantized or otherwise reconciled with quantum principles. The Planck scale tells us roughly where that missing theory will become necessary. This is why it is useful to think of the Planck scale as nature's smallest stage, but only if we remember what stage means in this context. It does not necessarily mean the smallest objects we can point to. It means the smallest arena in which our current play can still be performed before the scenery collapses and the script stops making sense. On larger stages, relativity can deliver its lines smoothly. On smaller stages, quantum mechanics can do the same, but at the Planck scale, the actors begin talking over each other. Gravity cannot be ignored, and quantum behaviour cannot be ignored, and so the old performance can no longer continue without a new director. There is a practical reason this has remained so difficult. The Planck scale is far removed from direct experimental reach in the usual sense. Human-built particle accelerators are magnificent instruments, but they are nowhere near the energies required to probe the Planck regime straightforwardly. Nature itself may produce conditions closer to it in the early universe, or near extreme gravitational objects, but those are not convenient laboratory environments. No one gets to reserve a black hole for the afternoon and adjust the settings between tea breaks. So much of what we know about the Planck scale comes from theory, dimensional reasoning, and the places where our current frameworks signal their own limitations rather than from direct observation in the ordinary experimental sense. Even so, indirect clues matter. Black hole thermodynamics, for example, has taught physicists that gravity, quantum theory, entropy, and information are deeply entangled in ways once thought separate. The existence of Hawking radiation, at least in theoretical prediction, suggests that black holes are not simply mute gravitational traps, but thermodynamic objects with temperature and entropy. That alone should make one suspicious of any simple division between the large and the small. A black hole, which seems at first like a purely gravitational entity, turns out to invite quantum considerations and deep questions about what information means in a physical universe. Once again, the Planck scale lurks nearby as the place where the full story will likely have to be told. The earliest universe pushes us in the same direction. Run cosmic expansion backward and everything becomes hotter, denser, and more compressed. Our models do a very good job for a great deal of that journey, but eventually the densities and times become so extreme that we approach the Planck regime. At that point, the usual account of spacetime as a smooth backdrop becomes doubtful. Asking what happened exactly at the beginning may be like asking what is north of the North Pole. The wording may carry an assumption that only works within a certain domain. This does not mean the question is foolish. It means the framework in which it is phrased may need revision. There is also something philosophically healthy about the Planck scale. It reminds us that human understanding is layered. We do not go from ignorance to final truth in a single leap. We build working descriptions, then discover their domain of validity. Newtonian mechanics remains enormously useful, but relativity and quantum mechanics show that it is not the deepest account. Relativity and quantum mechanics are themselves extraordinarily successful, yet the Planck scale suggests they too are incomplete when taken separately. In this way, physics becomes not a museum of discarded mistakes, but a hierarchy of approximations, each powerful within its range. The Planck scale is the sign at the edge of one such range, telling us that the road continues, though the current map does not. Because the scales are so extreme, they also cleanse the imagination of some lazy habits. We often picture emptiness as nothing at all, a passive void waiting for objects to move through it. But at the Planck scale, space itself may have properties, fluctuations, or structures that make emptiness a far more active notion than everyday language suggests. Time too may cease to be a smooth-flowing parameter and instead become something emergent or relational in a deeper theory. That possibility is one of the reasons the Planck scale has such a hold on the scientific imagination. It does not merely invite us to discover smaller things. It invites us to reconsider what space and time are. This is where popular images of the universe as made of tiny little bricks can become misleading. The Planck scale is not necessarily a tiny version of ordinary space. It may involve geometries, topologies, or quantum states that do not resemble our everyday picture at all. Some approaches to quantum gravity picture spacetime as emerging from more basic informational or algebraic relations. Others treat geometry itself as something quantized. Still others suggest that what we call space-time may arise from entanglement patterns or other underlying structures. The details are contested, but they all share a common lesson. At the Planck scale, asking what space is made of may be less useful than asking what kind of theory gives rise to the space we experience. That can sound frustrating, but it is also exciting in a disciplined sort of way. Physics is often most alive where its language becomes slightly inadequate. Not useless, but strained. The Planck scale is one of those regions where careful humility becomes a scientific virtue. We know enough to identify the frontier. We do not yet know enough to describe the territory beyond it with confidence. That is not failure. It is clarity about the edge of present knowledge. And now we can begin to see why this smallest stage matters so much for our larger question about the maximum possible force. Force is not merely a number that can be dialed upward without consequence. If you keep increasing intensity, compressing more energy into smaller regions, or pushing gravity into stronger and stronger regimes, you eventually approach the domain where space-time itself becomes part of the problem. The Planck scale is where the background stops being reliable background. Once that happens, the idea of force must be reconsidered alongside geometry, horizons, quantum fluctuations, and the possibility that nature enforces limits in ways more subtle than simply refusing to go higher. That is why the Planck scale is not a digression from the story of force. It is the stage on which the sharpest version of the question will eventually have to be asked. If there is a natural upper bound to force, it is not likely to reveal itself in a gymnasium, an engine room, or even an ordinary star. It will reveal itself where gravity, quantum mechanics, and relativity all speak at once. The Planck scale tells us where to listen. It marks the region where familiar descriptions reach their edge, and where the universe may begin to show whether force, like speed, comes with a built-in limit, or whether our current suspicion of such a limit is merely another stepping stone toward a deeper theory. If the Planck scale is the region where our current descriptions of nature start to strain, then Planck force is one of the sharpest numbers that emerges from that strain. It is a natural unit of force built not from human convenience, not from machinery, not from engineering practice, but from the constants that govern gravity and relativity. In that sense, it is not just another large force sitting somewhere above rocket engines and exploding stars on an imaginary leaderboard. It is meant to represent something more basic, a benchmark written into the logic of the universe itself, a kind of limit shaped not by what human beings can construct, but by how space-time and gravity permit influence to be concentrated. That is why the phrase "the universe's ultimate push" is both useful and slightly misleading. Useful because it gives the mind something concrete to hold for a moment. Misleading because Planck force is not literally a giant hand leaning on the cosmos with impossible determination. In physics, force is always tied to a situation. Something acts on something else. Motion changes, pressure builds, geometry bends, matter responds. Planck force is not a single event you can point to in nature and say, there it is, that exact push right there. It is a natural scale, a measure that tells us when the intensity of gravitational influence and relativistic structure are approaching a region where our usual descriptions are nearing their limits. One of the most interesting features of Planck force is that although it belongs to the family of Planck units, it is a little unusual among them. Many Planck quantities are introduced by combining the constants of quantum mechanics, gravity and relativity all together. That is part of what makes the Planck scale feel like the meeting place of the very small and the very massive. But Planck force has a curious simplicity. When you work through its definition, the quantum constant drops out of the final expression. What remains is built from the speed of light and the strength of gravity. That does not make it non-quantum in spirit, because it still belongs to the same natural unit system and still matters in the region where our theories are expected to meet. But it does give Planck force a distinct flavour. It sounds like a quantity from the deepest borderlands of physics, yet it speaks in a language particularly close to gravity and relativity. This is worth pausing over because names can quietly mislead us. When people first hear the phrase Planck force, they sometimes imagine that it must refer to a tiny force acting at tiny distances, perhaps something delicate and subtle, because the word Planck is so often associated with extremely small scales. But the force itself is not tiny, quite the opposite. It is staggeringly large, enormous on a scale so far beyond ordinary mechanical experience that comparison becomes an awkward business. It is the kind of quantity that makes even the violence of stars seem local and modest by comparison. Yet its origin is not in piling up larger and larger machines, or imagining ever more dramatic explosions. Its origin is in asking what sort of natural force scale appears when the constants of gravity and the speed of light are combined in the most direct way possible. There is something very elegant about that. Physics often discovers significance not by collecting the biggest examples, but by noticing that certain combinations of constants define thresholds that nature seems to care about. The speed of light is not just a fast thing. It is a structural limit on how information and causation move through space-time. The gravitational constant is not just a bookkeeping device for falling objects. It tells us how strongly mass and energy shape geometry. Put these ingredients together in the right way, and Planck force appears, not as human invention, but as a natural benchmark for how intense force can be in a universe with gravity and relativity built into its fabric. Now, it would be tempting at this point to make a grand dramatic declaration and say that Planck force is absolutely and unquestionably the maximum possible force in nature. That would be tidy. It would also be slightly too tidy. A more honest description is that Planck force is the natural force scale at which many physicists suspect some kind of upper bound or deep structural limit becomes relevant. There is a line of thought in general relativity, sometimes called the maximum force conjecture, suggesting that there may indeed be a universal upper bound to force and that the bound is closely related to Planck force, differing only by a modest numerical factor depending on the precise way one states it. This is a serious and intriguing idea, but it is not a universally settled law on the same level as the conservation of energy or the impossibility of outrunning light. It lives in a more speculative but still respectable zone, which is often where the most interesting questions live. So what exactly are we defining when we define Planck force? We are defining a natural unit of force that emerges from the constants of nature, especially gravity and the speed of light, and that seems to mark the scale where spacetime can no longer be treated as a passive stage under arbitrarily intense stress. If force grows too large in a region, gravity does not simply stand aside and allow the story to continue as if nothing has changed. Instead, gravity answers. Space and time curve more severely, horizons threaten to form, energy concentration begins altering the arena itself. In that sense, Planck force is not just about strength. It is about the moment when strength stops being merely a property of events happening in space-time and starts becoming a property that reshapes space-time. This makes it different from the sort of force scales we usually encounter. A car engine can produce a large force. So can a hydraulic press. So can an exploding shell or a launch vehicle leaving Earth. But these are all forces operating in a world where the background geometry is basically unbothered. Space-time does not care very much about your lorry, your bridge, or your regrettably enthusiastic fireworks display. Even stars, for much of their existence, manage their internal violence without calling the deeper structure of space-time into question. Planck force belongs to another class. It marks a regime where force is no longer just an intense local event. It becomes something tied to the architecture of the universe itself. One way to make sense of this is to remember that force in relativity is not quite the same sort of creature it was in older mechanics. In Newtonian thinking, force acts in space and time as though they were a fixed backdrop. In relativity, especially in general relativity, gravity is not simply one force among others. It is the curvature of space-time. That means very large concentrations of energy and momentum alter the geometry through which everything else moves. So if you try to imagine arbitrarily large force packed into a region, you're not just imagining a more extreme version of ordinary mechanics. You are imagining a situation in which the stage bends under the performers. At some point, the distinction between the act and the stage becomes impossible to maintain. That is the deeper meaning behind the idea of an ultimate push. If you continue trying to increase force without limit, nature may refuse not because it is delicate, but because the conditions required to exceed the limit would produce horizons or other geometric responses that change the physical situation entirely. It is a bit like asking how steep a mountain road can become before it stops being a road and starts being a cliff. The materials, shapes, and possible motions all change before the abstract increase can continue forever in the old way. There is also an important humility built into the concept. Planck force is not measured in the way one measures the force of a spring in a school laboratory. No one is constructing a machine to apply Planck force between two polished metal blocks while a graduate student checks the readout and looks concerned. The concept is theoretical. It arises from dimensional reasoning and from the structure of general relativity and natural units. Its importance lies not in direct everyday measurement, but in what it tells us about the scale where our physical descriptions become geometrically and gravitationally self-limiting. If you want a rough feel for how enormous it is, one can say that it corresponds to a quantity of force far beyond anything produced by human technology, and beyond the sort of forces we normally describe even in astrophysics. It is so large that if one tried to imagine it in familiar engineering terms, the imagination would quickly start behaving like a clerk handed a number with far too many zeros and no guidance on where the decimal point ought to live. This is why comparisons can mislead. The point is not merely that Planck force is bigger than a rocket or a star. It is that it belongs to a conceptual tier where ordinary comparisons stop being especially informative. That said, scale still matters. The reason Planck force is so large is not simply that nature likes dramatic numbers. It is large because gravity is ordinarily weak, and the speed of light is deeply fundamental. When these are combined into a force scale, the result is immense. A universe in which gravity was stronger, or the speed of light structured differently, would have different natural units, and perhaps very different large-scale behaviour. So Planck force is telling us something specific about our universe. It is not a generic badge of extremeness. It is the extremeness natural to a cosmos with this speed limit and this gravitational coupling. There is a quiet irony here. Gravity, at least at the scale of particles and everyday objects, is famously feeble compared with electromagnetism. A small fridge magnet can defeat the pull of the entire Earth on a paperclip. This has long encouraged the sense that gravity is somehow the weakling of the fundamental interactions, the shy cousin at the family gathering who mostly rearranges planetary orbits and avoids making a scene at the microscopic table. And yet, when gravity is allowed to act collectively over enough mass and enough concentration, it becomes the decisive sculptor of the largest and harshest structures in the universe. Planck force reflects that deeper authority. Gravity may be weak locally, but it governs the architecture of extremity. This is why discussions of Planck force so often drift toward black holes. Black holes are not just dramatic cosmic objects. They are among the clearest signs that gravity can impose structural limits. Squeeze enough energy into a small enough region, and an event horizon forms. At that point, the geometry itself announces that business as usual is over. If there is a maximum force conjecture worth taking seriously, black hole horizons are likely to be central to it, because they are exactly the sort of response nature gives when intensity becomes too concentrated. The limit is not enforced by a red light flashing in empty space. It is enforced by gravity changing the causal structure of the region. That gives Planck force a very different personality from the usual heroic language of maximums. It is not like the strongest bridge or the fastest sprinter or the loudest rock concert, all of which suggest competition within a stable world. Planck force belongs to a domain where the world itself becomes unstable under the conditions being asked of it. That makes it less of a record and more of a threshold. There is also the matter of interpretation. Some physicists emphasize Planck force as a natural unit and leave the question of an exact universal bound open. Others are more willing to connect it directly to the idea that nature permits no greater force than a value of this order. The difference is important. A natural unit tells you what scale is relevant. A strict upper bound tells you what is forbidden. Physics is not always eager to make the second claim, unless the first has very strong support. So the safest and most useful way to speak is to say that Planck force is the characteristic scale associated with any proposed maximum force in nature, and with the onset of regimes where space-time itself reacts decisively to concentrated intensity. That phrasing may sound cautious, but caution is often what keeps a subject interesting. It leaves room for what we know, what we strongly suspect, and what remains unsettled. It also protects us from turning a profound idea into a slogan. There is a tendency in science communication to flatten every deep concept into a certainty because certainty feels satisfying. But the real pleasure of physics often lies in the tension between mathematical elegance and physical interpretation. Planck force is elegant because it emerges so naturally from fundamental constants. It is compelling because it seems connected to horizons, relativity, and gravity under extreme stress. It is still intellectually alive because its exact role as a universal upper bound remains part of a larger and unfinished conversation. Even with that caution, the concept has enormous explanatory value. It tells us that if we keep asking how much force nature can sustain, we are not climbing an infinite ladder inside a fixed box. We are approaching a regime where the box bends. That changes the question. Force can no longer be discussed as though space and time were indifferent spectators. They become participants. Once that happens, the idea of an ultimate force stops sounding like a simple engineering limit and starts sounding like a statement about the structure of reality. And there is something almost reassuring about that. A universe with a maximum speed already feels more coherent than one in which signals can travel arbitrarily fast. A universe with meaningful Planck scales feels more coherent than one in which all quantities can be pushed without end while the background remains passive. Limits in physics are not always restrictions in the dreary sense. They're often the things that give the world shape. They tell us what sorts of events can happen, and what sorts of events require the rules themselves to transform. So Planck force, properly understood, is not just the biggest shove imaginable. It is the natural force scale at which gravity, relativity, and the concentration of energy stop allowing us to pretend that force is merely something happening inside space-time. Instead, force begins to threaten the very structure through which causes and effects are organized. It is the point where intensity becomes geometry, the point where pushing harder may no longer mean more of the same, but something categorically different. And once that definition is in place, another question arrives almost immediately. If Planck force marks the relevant scale for a possible upper limit, why is it so absurdly enormous? What is it about the constants of nature, and especially about gravity and light, that puts this benchmark so far beyond anything our daily experience would ever suggest? That question matters because it takes us from the definition itself into the deeper character of the universe that produced it. One of the strangest things about Planck force is not merely that it is large, but that it is large in a way that feels almost rude. It does not sit a little above the strongest forces we know from engineering, or a little above the violence of stars, or even a little above the more dramatic phenomena of astrophysics. It towers over them. It belongs to a scale that makes almost every ordinary example of force look provincial. And because the name comes wrapped in the quiet language of fundamental physics rather than the loud language of explosions, people are sometimes caught off guard by just how enormous it really is. That surprise is useful. It tells us that our intuitions about force are deeply local. We are creatures of moderate scale. We live among tables, weather, vehicles, buildings, mountains, and oceans. Even when we stretch our imagination toward the more energetic parts of nature, we tend to think in terms of what still feels like bigger versions of familiar events. A larger impact, a hotter fire, a heavier object, a greater pressure. Yet Planck force does not arise by scaling up everyday life. It emerges from the structure of the universe itself, and that structure is under no obligation to match the psychological range of a species that developed by throwing stones and occasionally misjudging ladders. So why is it so enormous? The shortest answer is that it is built from ingredients that are themselves profound. It reflects the relationship between gravity and the speed of light, and that relationship produces a force scale that is not tuned to human experience, but to the deepest architecture of space-time. That sounds grand, but there is a more grounded way into it. The sheer size of Planck force tells us that gravity, when translated into a natural upper scale consistent with relativity, allows everyday life to be astonishingly calm by comparison. Our local world is not perched near the limit. It exists very comfortably below it. This is worth appreciating because there is a tendency to assume that fundamental scales ought to feel somehow close to home. We imagine that if something is basic, it should be easy to see in ordinary life, as though the foundation of a house ought always to peek through the carpet. But physics often works the other way around. The most fundamental scales can be so remote from everyday conditions that they reveal themselves only through theory or under extreme circumstances. The speed of light is a basic feature of reality, yet it does not feel basic while walking to the shop. Quantum effects shape matter at every moment, yet chairs continue looking reassuringly unquantum unless one becomes unusually philosophical about upholstery. In the same way, Planck force can be deeply fundamental without being anywhere near the range of ordinary encounter. There is also the peculiar character of gravity to consider. Gravity has a double identity in physics. Locally, in the microscopic world and in daily life, it often seems weak. That weakness is not an illusion. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. A comb rubbed on cloth can attract tiny bits of paper more effectively than gravity can hold them still. If one were judging only by such scenes, gravity would seem almost embarrassingly gentle, a force whose main talent is making dropped items hard on the floor and mildly inconvenient for the knees. But this local weakness is paired with a remarkable global authority. Gravity is always attractive in the ordinary macroscopic sense. It does not come with positive and negative versions that cancel one another in the easy way electric charges can. It accumulates, it gathers, it becomes decisive wherever enough mass and energy are involved. Stars form because gravity collects gas. Galaxies hold together because gravity shapes their motion. Black holes exist because gravity, once given enough concentrated matter, does not back down simply because the consequences become unfashionably extreme. So the weakness of gravity at small scales and its dominance at large scales are not contradictions. They are two sides of the same story. Planck force sits at the far end of that story. It reflects what happens when gravity is considered not as the mild, downward pull we spend our childhood learning to stop underestimating, but as a structural feature of space-time under the most severe possible conditions. In that setting, the weakness of gravity and particle interactions is no longer the important fact. The important fact is that gravity determines when energy concentration stops being just another event and starts reshaping the arena itself. That is one reason the natural force scale ends up so large. It is tied to the threshold at which geometry must respond. The speed of light matters here too, and perhaps more deeply than it first appears. The speed of light is not just the speed of light in the parochial sense, as though it were merely a property of one especially athletic phenomenon. It is the fundamental speed built into causality and relativity. It determines how influences propagate, how time and space are related, and how mass and energy enter into the same overarching framework. So when a natural force scale includes the speed of light in an essential way, that force scale is already speaking about the deepest limits of process in the universe. It is not describing the pull of a rope or the thrust of an engine. It is describing a boundary condition for how intensely the structure of space-time can be asked to mediate change. This gives us a hint about why the number comes out so large. Force is, in a sense, the concentrated expression of change. It tells us how strongly motion is altered. But if the universe allows enormous amounts of energy to exist and enormous structures to form, while also imposing a fixed causal speed and a specific gravitational coupling, then the natural scale where those features meet can easily lie far above ordinary circumstances. Everyday forces are modest, not because force itself is a small thing, but because the arrangements of matter around us are mild. Chairs are not neutron stars. Kitchen tables are not event horizons. Most of the universe, including the part we regularly complain about stepping on, is not operating at the edge of geometric collapse. Another way to say this is that Planck force is enormous, because our universe is spacious. Not spacious only in the astronomical sense, though it is certainly that, but spacious in the dynamical sense. It leaves a vast gulf between daily physical processes and the scale where space-time itself becomes violently implicated. This gulf is part of what makes stable chemistry, long-lived stars, planets, weather, geology, and eventually life possible. If the fundamental force scale relevant to gravitational breakdown were much lower, the universe might be far less forgiving. Matter could cross into exotic regimes too easily. Stars might behave differently. Structures that now live peacefully for billions of years might instead be constantly flirting with catastrophe. The enormous size of Planck force is therefore not just a curiosity. It is part of what makes our relatively gentle region of existence possible. It also tells us something about the hierarchy of nature. Physics is full of these hierarchies. Atoms are tiny compared with grains of sand, yet still large compared with nuclei. Nuclei are large compared with the scales at which the deepest quantum gravity questions begin to appear. Human speeds are tiny compared with the speed of light. Human temperatures are tiny compared with stellar interiors. Human lifetimes are tiny compared with stellar ages, and huge compared with many subatomic processes. The universe is not organized around the middle. It is organized across vast ranges. Planck force sits very high in one of those ranges, and its enormity is another reminder that the cosmos is not calibrated to our convenience. Now, there is an understandable temptation to compare Planck force directly with the strongest forces produced in human technology. Rockets, particle beams, high-pressure devices, explosives. These comparisons can be fun for a moment, but they usually mislead after that. Human machines produce impressive forces in specific contexts, yet they do so in regimes where matter remains matter in the familiar sense, where materials still have recognizably ordinary properties, and where gravity barely notices. Planck force belongs to a domain where the question is no longer how sturdy the material is, or how efficient the design might be. The question becomes whether spacetime itself allows the situation to continue in the same category. In that sense, comparing a launch vehicle to Planck force is a little like comparing a violin string to the tectonic structure of a planet. Both involve tension of some sort, but the conceptual worlds they belong to are very far apart. This same caution applies even in astrophysics. Stars are fierce, but most of their violence is still orderly by the standards of fundamental limits. A main sequence star holds itself together through balance. Even a supernova, catastrophic as it is, unfolds according to processes that remain well below the threshold, where one must invoke a natural upper force scale in a direct way. Neutron stars and black holes bring us much closer to the relevant territory, because they involve gravitational compression so severe that matter is pushed into forms alien to ordinary experience. But even there, what matters is not merely that the forces are large. It is that they are large enough to make the geometry of space-time inseparable from the description. This is why black holes are such useful guides when trying to understand the size of Planck force. A black hole is nature's way of telling us that concentrated energy cannot simply be increased forever inside an unchanged spatial arena. Compress enough mass or energy into a small enough region, and the response is not just more of the same. An event horizon forms, causal structure changes, paths that once led outward no longer do. The geometry has answered the concentration. If there is a meaningful maximum force principle, it is likely enormous precisely because the universe permits very intense conditions before such a response becomes unavoidable. But once the response becomes unavoidable, it is decisive. There is something almost architectural in this. Imagine building taller and taller arches of stone. At low heights, the stone simply bears the load. At greater heights, the forces within the structure become more severe, and eventually the design itself must change or collapse. Planck force is not the weight borne by one more brick on top of the arch. It is more like the natural scale at which the structure of the building material and the geometry of the whole construction can no longer be treated separately. In our universe, that architectural threshold is extremely high. That is another way of saying that Planck force is enormous. A subtler reason for its size lies in the fact that our universe contains very different regimes that nevertheless coexist without immediately destroying one another. The microscopic world is governed by quantum principles. The large-scale world is governed by gravity and relativity. Chemistry proceeds, stars shine, galaxies rotate, light crosses vast distances. All of this suggests that the bridge point where the smooth description of space-time breaks down has to lie far enough away from ordinary conditions to allow these domains to remain stable in their own ranges. If the bridge point were too close, our neat separation between everyday mechanics, quantum behavior, and gravitational structure would fail constantly. Instead, the universe gives us an enormous buffer zone. Planck force reflects the existence of that buffer. One might also say that Planck force is enormous because the universe is surprisingly tolerant before it becomes radically intolerant. It allows matter to clump, stars to ignite, nuclear processes to run, compact remnants to form and vast gravitational systems to evolve. It does not intervene at the first sign of ambition, but when concentration becomes too extreme, it responds in kind. The fact that the response point is so high means the cosmos has a broad middle range where complexity can unfold. That broad middle range is where planets exist, where rocks remain rocks, and where people can argue late into the evening about physics instead of being crushed by runaway geometry every time they move a sofa. This scale separation is also one reason why the idea of a maximum force can sound unbelievable at first. We do not experience daily life as though force were limited in some profound universal way. We experience it as though objects simply break, bend, move, or resist according to material circumstances. That is true within our regime, but material failure is not the same thing as a fundamental limit. A steel beam buckles for reasons rooted in atomic bonding, structure, and stress distribution. That is a local and contingent limit, not a universal one. Planck force concerns a much deeper question. It asks when force becomes so intense that the universe itself, through gravity and space-time structure, imposes a boundary independent of the particular material details. There is another odd comfort in the largeness of Planck force. If the fundamental limit were close to everyday conditions, the universe would likely feel cramped. Instead, it feels open. There is room for hierarchy, room for processes to operate at different scales, room for stars to spend long lives in equilibrium, and for planets to orbit in relative calm. The enormous size of Planck force is one expression of that roominess. It tells us that the cosmos permits an immense range of phenomena before the deepest architectural constraints become unavoidable. At the same time, the very existence of such a scale hints that this roominess is not infinite. There is freedom, but not boundlessness. There is headroom, but not without ceiling, and that balance may be one of the most interesting features of the universe. Too low a ceiling and complexity might never flourish. No ceiling at all, and perhaps space-time would allow pathologies or instabilities that our current theories do not know how to handle. The actual world seems to live between those extremes, generous in range, strict at the edges, so Planck force is enormous because it does not describe the strongest thing we happen to have seen this week. It describes a natural threshold tied to gravity, causality, and the concentrated structure of space-time. It is enormous because gravity is weak in local interactions, but sovereign in the architecture of large-scale extremity. It is enormous because the speed of light sets a deep causal scale. It is enormous because the universe leaves a vast gap between ordinary physical life and the point where geometry itself must answer the intensity of events. And it is enormous because the cosmos, though full of violence, saves its most serious restrictions for conditions so severe that only the densest and most extreme objects come near them. Which means that to understand Planck force properly, we cannot stop at the word force alone. We have to follow gravity into the places where it stops being merely one influence among others and starts dictating the shape of reality itself. That takes us naturally toward black holes, compression, and the strange suspicion that the ultimate limit on force may be inseparable from the ultimate limit on how tightly the universe allows energy and matter to be packed. Gravity is easy to underestimate because it is so patient. It does not flash like lightning or crack like a gunshot or announce itself with the sort of theatrical confidence people usually associate with great power. It simply continues. Day after day, century after century, it keeps pulling. It gathers dust into pebbles, pebbles into rocks, rocks into worlds. It draws gas into clouds, clouds into stars, stars into systems and galaxies. It is not loud, but it is relentless, and that combination turns out to matter more than volume. A weak influence that always adds and never tires can eventually become the most important fact in the room. That is the first thing to keep in mind when we turn from Planck force in the abstract to gravity in its most severe forms. The enormous natural scale we have been discussing is not most likely to show up in the world of ordinary contact forces. It does not belong naturally to gears, pistons, bridges, or even the pressure inside most stars. It belongs where gravity has had enough time, enough mass, and enough freedom to keep compressing matter until the very structure of space and time starts responding in ways that our daily experience cannot prepare us for. Black holes are the clearest sign that this kind of response is real. They are nature saying that compression cannot go on forever inside a passive stage. At some point, the stage itself changes. Compression is one of those words that sounds harmless until physics takes it seriously. In ordinary life, compression means squeezing something smaller. A sponge compresses under your hand, a spring compresses in a machine, a pillow compresses and then does a mediocre job of recovering its dignity. Matter feels squashable or rigid depending on what it is made of and how hard you press. Most of our intuitions about compression come from materials that remain more or less themselves while changing shape. But gravity deals in a more ambitious sort of compression. It does not just flatten or dent things. Given enough mass, it can force matter through a whole sequence of transformations. A cloud of gas in space begins as something very diffuse. Gravity pulls it inward. As the cloud contracts, it heats up. Pressure rises. If enough mass is present, a star forms. Already gravity has converted broad thin matter into a dense, hot, luminous object. Yet even there the process is not complete. The star resists further collapse through internal pressure generated by nuclear processes. For a while there is balance. Gravity pushes inward. Pressure pushes outward. The star shines because those two influences are locked in a long truce. But a truce is not peace. It is a maintained tension. And if the outward support weakens, gravity resumes the argument with full memory of what it wanted all along. This is what makes stellar collapse so important to our question. It is the place where gravity stops being the gentle organizer of large-scale structure and becomes the engine of severe compression. A dying star may collapse into a white dwarf, where matter is packed into a state supported not by ordinary thermal pressure, but by quantum mechanical resistance among electrons. If the mass is too great for that to hold, collapse continues and a neutron star may form, where matter is crushed so intensely that electrons and protons are driven into a radically denser arrangement dominated by neutrons. In each case, compression is not just making matter smaller, it is changing what sort of matter the object is. This sequence already tells us something very important. Nature does not allow a simple, infinite scaling of ordinary substance. Matter answers compression by changing regime. Atoms give way. Electron structure gives way. Familiar solid, liquid, and gas distinctions cease to matter. New kinds of pressure emerge. New forms of organization appear. So when people ask how much force or pressure matter can withstand, the honest answer is not a single material property. It is a story of transitions. Compression keeps revealing deeper layers of resistance until perhaps, in the most extreme cases, resistance of the familiar kind is no longer enough. Black holes stand at the far edge of that story, at least within general relativity. They are what happens when gravity is allowed to compress matter or energy beyond every known stabilizing mechanism. A black hole is not just a very dense object in the way a neutron star is a very dense object. It marks a qualitative change. There comes a point where the concentration of mass and energy becomes such that an event horizon forms. That phrase, event horizon, has become so common that it sometimes loses its strangeness, but it deserves to be heard freshly. It is a boundary in space-time, not a hard surface like the outer shell of a planet. Once crossed, it marks a region from which no signal can escape outward to distant observers. Not light, not matter, not a hasty apology. This matters profoundly because it changes what we mean by compression. Before a horizon forms, one may still imagine asking how tightly matter is packed inside an object, what pressure supports it, what material state it occupies. After a horizon forms, the conversation shifts. General relativity tells us that the geometry has become so severe that escape routes outward no longer exist. The object is no longer simply compressed matter sitting in an ordinary environment. It is a region whose causal structure has changed. That is why black holes are central to any serious discussion of maximum force or limit of compression. They are the clearest sign that if you try to concentrate energy too much, gravity does not merely permit more of the same, it changes the category of the thing you're discussing. There is something almost judicial about that. Up to a point, nature allows compression and responds with denser states of matter. Beyond a point, it responds with horizons. It is as though the universe says you may keep squeezing, but only until the squeeze becomes a geometrical event rather than merely a material one. This is one reason black holes often appear in discussions of Planck force and the possibility of a universal upper bound on force. They are not evidence of large force only. They are evidence that large force and concentrated energy invite structural consequences from spacetime itself. To understand why, it helps to step back and remember what gravity is in general relativity. It is not merely one body pulling on another across empty space in the old Newtonian sense. It is the curvature of space-time produced by mass and energy. Objects move along the paths available within that curved geometry. That description is elegant when discussing orbits and falling bodies, but it becomes truly dramatic when curvature becomes extreme. Near a black hole, the paths available to matter and light are bent so strongly that the notion of ordinary escape becomes meaningless once the horizon is crossed. Geometry itself has become the dominant fact. That is why compression and gravity cannot be separated at the highest levels. If you try to increase force by packing more and more energy into a region, you're also increasing the gravitational role of that region. If the concentration becomes great enough, you do not just get a stronger local event, you get a space-time configuration that changes what counts as possible motion. This is the deeper reason that black holes loom over the subject. They show that there is a built-in gravitational answer to excessive concentration. There is also the matter of escape speed, which offers an intuitive bridge into the subject even though the full story requires relativity. In the older picture, one can imagine a body so massive and compact that the speed required to escape its gravitational pull becomes greater than the speed of light. That image is not the modern definition of a black hole, but it gives a useful hint. If the speed needed to get away exceeds the universal speed limit, then no outward travel is possible. General relativity replaces this with the richer language of causal structure and horizons, yet the intuition remains helpful. There is a point where gravity becomes so severe that the very notion of leaving is no longer part of the local future. Once that point is reached, the idea of further compression becomes more delicate. To an outside observer, the black hole is characterized by properties such as mass, spin, and charge, not by a visible interior state in the ordinary sense. What is happening inside becomes a more dangerous question, because our current theories begin giving answers that are physically troubling. Classical general relativity predicts that continued collapse leads toward a singularity, a place where curvature becomes unbounded, and the theory itself effectively signals that it has been pushed beyond its proper domain. Most physicists take this not as the final literal story, but as evidence that a deeper theory, likely involving quantum gravity, is needed. That is exactly why black holes are so valuable here. They are not just exotic objects. They are where our best theory of gravity drives itself to the edge of its own competence. And when a theory as successful as general relativity says that further compression leads to a breakdown, one should pay attention. It suggests that the limit of compression is not merely a material question about how much a given substance can withstand. It is a theoretical question about where the smooth geometrical picture of space-time must give way to something deeper. This brings us closer to the notion of maximum force without requiring us to pretend that the matter is fully settled. Suppose you try to transmit ever larger and larger force across a region. In a simple world with fixed background space and time, perhaps you imagine that the force can keep growing indefinitely. But in our world, where gravity couples to energy and momentum, concentrated intensity has geometric consequences. Too much concentration across too small a region and you form a horizon. That means that what looked like a question about bigger and bigger force turns into a question about black hole formation. The limit is not imposed by a sign saying no entry. It is imposed by the geometry closing over the process. Some physicists have taken this idea seriously enough to propose that there is a maximum force in nature closely related to the scale set by relativity and gravity and associated with horizons. The precise statement can vary, and the status of the conjecture remains debated, but the intuition is strong. Horizons appear to encode a kind of ceiling on how intensely force or power can be transmitted in an unconcealed way through spacetime. If you push too far, spacetime responds by hiding the region behind a horizon. The event is no longer simply a larger visible interaction. It has changed into something else. This is deeply satisfying because it links force not only to matter, but to information and visibility. A black hole is not merely dense, it is informationally strange. From the outside, much of the detailed story of how it formed is hidden. That means the limit of compression is tied not just to strength, but to what the rest of the universe is allowed to know and influence. In a sense, horizons are nature's way of saying that beyond a certain concentration, the inner story can no longer remain part of ordinary causal exchange. There is another reason compression matters so much here. Force is often easiest to picture as something spread over time and distance. Push a cart, stretch a rope, press a spring, but in extreme gravity, distance itself becomes treacherous. Near a black hole, spatial intervals and temporal intervals do not behave in the ordinary way from the viewpoint of distant observers. Time slows relative to faraway clocks. Paths curve dramatically. Tidal effects can become enormous. The same physical event no longer admits a simple common-sense description. So the closer one gets to the limit of compression, the less useful naive images of force become. One has to think geometrically. One has to think in terms of horizons, curvature, and the reshaping of causal possibility. Tidal forces deserve a brief pause here because they show that gravity is not just about overall pull, but about differences in pull from one location to another. Tides on Earth are gentle enough to inspire seaside holidays and occasional damping convenience. Near compact objects, the same principle becomes much more severe. One part of an object can be pulled far more strongly than another. Stretching and squeezing follow. In some black hole environments, these tidal effects become destructive long before any horizon is crossed. In others, especially around very massive black holes, the horizon can be crossed locally without immediate drama, though escaping afterward remains impossible. This reminds us that black holes are not all identical in practical experience, even if their essential role in the limit of compression remains the same. And then there is the early universe, which offers a kind of reverse image of gravitational compression. Instead of matter collapsing inward from a star, we imagine the cosmos in its earliest accessible phases as immensely hot, dense, and compressed. Run cosmic history backward and one approaches conditions where our usual distinction between matter in space-time and the structure of space-time itself becomes increasingly unreliable. Here too, the limit of compression becomes not just a question of matter, but of the viability of the geometrical framework. Black holes show this limit in localized form. The early universe suggests it may once have been universal. That parallel is important because it tells us the problem is not peculiar to one dramatic object type. It is woven into the meeting point of gravity, density, and the structure of reality. Whether in collapse or in the earliest expansion, extreme concentration pushes us toward the same frontier. The smooth stage of general relativity begins to look provisional. The limit of compression becomes the limit of our present language. At the same time, one should avoid the mistake of thinking that every kind of large force immediately means black holes and singularities. The universe is capable of many intense processes that stay comfortably short of that threshold. What makes black holes special is not merely magnitude, but concentration. Mass and energy must be packed sufficiently tightly for the horizon response to occur. This keeps the concept physically meaningful rather than melodramatic. Nature is not so fragile that it produces horizons every time something interesting happens. It is permissive over a vast range, then strict beyond that. That pattern is exactly what one would expect if a deep upper bound or structural limit is present. Compression therefore serves as a bridge between the intuitive and the ultimate. Everyone understands, at least in rough terms, that squeezing something changes it. Physics extends that truth until it reaches astonishing consequences. Squeeze a gas cloud and you get a star. Squeeze a dying star far enough and you may get a white dwarf or a neutron star. Squeeze still beyond all known support and a black hole forms. Follow the mathematics farther and it begins to fail, which is itself a kind of information. It tells us that the question how much compression is possible cannot be answered forever within the same theory. The universe is indicating that beyond some point, the old description is no longer the right one. And that is perhaps the most important lesson black holes offer to the question of maximum force. They show that extremity is not just about bigger numbers, it is about phase changes in the rules. At mild scales, force changes motion. At more severe scales, force changes matter. At the most severe gravitational scales, concentrated force and energy begin changing spacetime itself. Once that happens, the idea of a simple unbounded increase becomes hard to defend. The world answers by reorganizing the conditions under which force can even be discussed. So gravity, black holes, and the limit of compression all belong together because they describe the same deep tendency from different angles. Gravity is the agent that accumulates and compresses. Compression is the process that forces matter through successive layers of resistance. Black holes are the space-time response when concentration passes a critical threshold, and beyond that threshold lies the suspicion that our present concepts are only approximations to something deeper, something that will have to explain not only what black holes are, but why the universe seems to enforce its most dramatic limits through geometry itself. That is where the discussion naturally begins leaning toward a still stranger question. If horizons and collapse prevent arbitrary concentration, what exactly breaks first when force keeps rising? Is it matter? Is it space-time? Or is it the ordinary common-sense distinction between the two? By the time force reaches the sort of extremes that concern compact stars and black holes, it stops being useful to think of breaking in the simple, everyday way. In ordinary life, something breaks when its material structure can no longer cope with the stress being placed on it. A twig snaps, glass shatters, a chair leg gives way at the least diplomatic moment possible. These are clear examples of failure, and they belong to a world where matter still behaves like matter we know. It bends, strains, cracks, and separates. The parts may fly about in an impolite fashion, but they remain recognizably the same kind of stuff. Wood stays wood, glass stays glass. Even when it breaks badly, it still belongs to the same family of behavior. Extreme physics is not so modest. There, breaking does not always mean fracture. Very often it means the collapse of one whole level of description into another. Matter does not merely crack, it stops being describable in the way it was before. The structures we use as our basic furniture of reality, atoms, nuclei, solid surfaces, ordinary space, ordinary time, begin to lose their authority. And when that happens, common sense, which is really just well-trained intuition for moderate conditions, starts making very poor guesses indeed. A useful place to begin is with the breaking of ordinary matter. If you squeeze a familiar object hard enough, the first things to fail are not the ultimate constituents of nature, but the arrangements that gave the object its familiar character. The shape changes. Bonds between atoms strain. Crystals deform. Molecules rearrange. Heat builds. Pressure redistributes. There is already a great deal going on in what we casually call breaking. A steel beam under too much load does not simply wake up one morning and decide it has had enough. Microscopic dislocations move. Grain boundaries matter. Stress concentrates in weak regions. The material yields or fractures according to deep but ordinary rules of atomic structure. Engineering is full of such subtleties. It is one of the reasons bridges deserve respect and furniture instructions deserve at least a quick glance before optimism takes the lead. But these are still events within the regime of chemistry and ordinary condensed matter. The atoms remain. The electrons remain bound in more or less familiar ways. Even high-pressure experiments on Earth, impressive as they are, usually remain in a territory where matter is exotic but still recognizably atomic. Push much harder, though, and the story changes. In the interior of giant planets and stars, pressure becomes so severe that atoms no longer look like tiny solar systems with polite empty space around them. Electrons are forced into behavior that cannot be captured by household intuition. Matter may become ionized plasma, metallic hydrogen, degenerate electron matter, or other high-pressure states that sound as if they were invented by a committee determined to make breakfast conversation more difficult. Already common sense is slipping. We like to think of atoms as little durable units, the smallest stable beads from which everything else is built. This is a useful fiction at mild scales and an increasingly poor one under severe compression. Atoms survive only as long as the conditions allow their electronic structure to remain meaningful. In a white dwarf, for example, matter is so compressed that one does not describe it in the language of ordinary solids or gases. Electrons are no longer sitting comfortably in the sort of atomic arrangements familiar from chemistry. Instead, quantum rules about occupancy and degeneracy become decisive. The matter resists further collapse not because it is springy in a familiar sense, but because quantum mechanics places restrictions on how identical particles can be packed into states. This is a very different kind of breaking. The atoms have not exploded into theatrical debris. They have been pushed past the usefulness of atomic language. Chemistry has given way to something more severe. If one insisted on using common sense here, one would likely imagine tiny balls being squeezed together until they touch. That is not terrible as a first image, but it misses the deeper truth. The resistance comes not from little hard shells pressing back in the way billiard balls might, but from the structure of quantum states. In other words, what breaks first is not matter itself, but our simple picture of what matter is. Push still harder, and even that regime yields. In the formation of a neutron star, the densities become so high that electrons and protons are driven into transformations that make neutron-rich matter possible on a vast scale. Here the language of intact atoms is entirely gone. Even the language of neatly separate nuclei surrounded by electron clouds has long since left the building. Matter has become something far more compressed and far more alien to everyday understanding. The forces at work are no longer those of materials science or ordinary plasma physics. Nuclear and quantum effects dominate. Pressure is no longer simply the agitation of particles bouncing about in a box. It is woven into the very possible states matter is permitted to occupy. This is the first sense in which forces break matter. They do not always smash it into pieces. They often force it to abandon one organizing principle for another. Molecules cease to be useful. Atoms cease to be useful. Familiar nuclei may cease to be sufficient. Under even more extreme and speculative conditions, perhaps inside the deepest parts of neutron stars, the matter may enter phases we still do not fully understand. Quarks may cease to remain confined into neat proton and neutron packages. Other exotic states may emerge. Physics becomes tentative there, not because nothing is happening, but because too much is happening for our present certainty to remain tidy. Now, if the story ended with matter-changing state under pressure, it would already be remarkable. But gravity does not stop at breaking matter. It moves on to breaking the comfortable distinction between matter and the stage in which matter sits. That is the truly unsettling part. For most of our daily lives, we imagine space as the passive place where events occur. Chairs sit in space. People walk through space. Stars shine in space. Time passes independently while all this goes on, and space simply remains available like an exceedingly patient landlord. General relativity taught us that this picture is incomplete even under ordinary conditions. Space and time are not just an empty container, they are dynamic and responsive. Still, It is only in strong gravity that this becomes impossible to ignore. Near a black hole, or during the collapse that forms one, space-time is no longer a polite background. It is part of the event. Paths curve so severely that light itself can be trapped. Clocks in different locations no longer tick in ways that line up with everyday intuition. Distances become slippery concepts depending on how and from where they are measured. The very idea of what it means for one thing to be inside or outside, before or after, reachable or unreachable, becomes more subtle. This is the second sense in which force breaks reality as we usually picture it. It does not merely damage objects, it damages the usefulness of our ordinary map of space and time. The event horizon of a black hole is one of the clearest examples of this. From far away, one can describe the horizon as a boundary beyond which escape is impossible. That is accurate, but it sounds almost too calm for what it implies. Escape is not impossible because there is a physical wall there. It is impossible because the geometry of space-time has been altered so deeply that all future-directed paths lead inward rather than outward. This is not the sort of thing common sense is built to picture. We are accustomed to walls, cages, locked doors, and bureaucratic procedures. We are less accustomed to regions where the future itself tilts in one direction. And then, just when common sense is already feeling underpaid, black holes introduce another insult. To a distant observer, objects falling toward the horizon appear increasingly slowed by gravitational time dilation. Their signals grow redder and fainter. It can look from that distant viewpoint as though the infalling object never quite finishes crossing in any ordinary visible sense. Yet for the falling object itself, there is no magical pause at the horizon, at least not in the simple dramatic way often imagined for sufficiently large black holes. It crosses and continues inward. Both descriptions belong to the physics. Neither fits neatly into the instincts we build from watching buses arrive and waiting for kettles to boil. This is what happens when force breaks common sense. It is not that logic disappears. The universe remains perfectly capable of being described. It is that the descriptive framework which served so well in moderate conditions can no longer be trusted unexamined. Simultaneity becomes relative. Distance depends on geometry. Time depends on gravity and motion. Escape is a matter of causal structure rather than muscular effort. The world has not become irrational. It has become more precise than intuition ever needed it to be. There is a further level of breaking still, and this is where the subject begins leaning toward the deepest frontier. Classical general relativity predicts that complete gravitational collapse leads towards singularities. A singularity, in the simplest summary, is a place where quantities such as curvature become unbounded, and the theory stops delivering physically sensible answers in the ordinary way. This is sometimes misheard as meaning that the universe literally contains points of infinite density waiting patiently inside black holes like theological footnotes. A better way to think about it is that the theory is signalling its own breakdown. It is saying, in effect, I've been pushed too far. The conditions you're asking me to describe require a deeper framework. This is the third and perhaps most serious sense in which force breaks things. It can break theories. If gravity compresses matter so far that our best classical account predicts singular behaviour, then what has failed is not simply an object or a material phase. What has failed is a description that was extraordinarily successful everywhere else. That should make one sit up a little straighter. When a great theory breaks, it is not a small inconvenience. It is a clue of the highest order. The likely suspect waiting in the wings is quantum gravity, the still incomplete framework that ought to describe situations where quantum effects and severe space-time curvature both matter at once. The Planck scale is where we expect such a theory to become unavoidable, and it is no coincidence that the questions of maximum force, ultimate compression, and singular behaviour all drift in that direction. Once forces become strong enough to threaten the smoothness of space-time itself, one cannot keep matter and geometry in separate conceptual drawers. The drawers have merged, the cabinet is on fire. New furniture is required. This is where everyday language begins offering metaphors that are useful for a sentence or two, and then should be shown the door before they start making trouble. One popular image is that space-time might become foamy or granular at sufficiently small scales. That can be helpful if it reminds us that smoothness may fail, but one must not imagine literal soap bubbles or a cheerful bath product version of quantum gravity. The deeper point is that the calm continuum we use in ordinary relativity may be an approximation, much as a wooden table looks smooth from a distance, even though up close it has grain, texture, and microscopic structure. If forces become extreme enough, perhaps the grain of space-time itself begins to matter. Whether space truly becomes discrete, or whether something even stranger replaces our current ideas, remains unsettled. Different approaches to quantum gravity tell different stories. Some suggest quantized geometry. Some suggest space-time emerges from more basic relations. Some lean on entanglement, information, or algebraic structure rather than literal tiny building blocks. But all of them are trying to address the same crisis. When force and compression become severe enough, the old common-sense picture of matter moving through a smooth backdrop stops being credible. There is another reason common sense suffers here. It evolved to deal with medium-sized objects moving at low speeds in weak gravity over moderate times. It is very good at helping one avoid walking into doors, though even there the success rate is not perfect. It was not designed to imagine degenerate matter, event horizons, or curvature becoming dynamically inseparable from energy concentration. So when people first encounter these ideas and feel that they sound absurd, that is not a failure of intelligence. It is a reminder that intuition is a local adaptation, not a universal authority. Physics becomes strange not because the universe enjoys showing off, but because the range of conditions it permits vastly exceeds the range in which human intuition was trained. Even causality can begin to feel under pressure in these discussions. Black holes hide information behind horizons. Quantum mechanics raises difficult questions about what information means and whether it is preserved. Time becomes less absolute. Simultaneity becomes observer-dependent. Near singular regimes, one cannot always trust the clean separation between cause and effect inherited from ordinary life. None of this means the universe permits arbitrary nonsense. Quite the opposite. It means the rules are more rigid and subtle than the rough categories of common speech. What breaks is not order, but our easy way of talking about it. There is also something humbling in the fact that matter itself is not fundamental in the simple, everyday sense. We grow up thinking substances are primary. Wood, metal, water, flesh, stone. Then science teaches that these are arrangements of molecules and atoms. Push harder and atoms are arrangements of nuclei and electrons. Push into nuclear scales and the distinction shifts again. Push into the regime of strong gravity, and perhaps even the geometry in which all such arrangements are described becomes emergent rather than fundamental. At each stage, what seemed basic becomes conditional. Forces reveal this by stripping away layers of stability one after another. One could almost say that force is reality under cross-examination. Under mild questioning, matter gives ordinary answers. Under stronger questioning, it admits to atomic and quantum structure. Under more severe questioning, it admits that atoms are not final, nuclei are not final, and perhaps smooth space-time is not final either. By the time the interrogation reaches black holes and Planckian regimes, the witness has abandoned ordinary language and is asking for legal counsel. This is perhaps as close to humour as such matters comfortably permit, but the point stands. Extreme force is not just big force, it is force capable of revealing that the categories we trusted were provisional all along. That helps explain why the subject is so compelling. It is not merely an arms race of larger numbers, it is an investigation into what remains meaningful when our best descriptions begin to fail. Matter breaks by changing phase and losing familiar structure. Space breaks by ceasing to behave like a passive stage. Common sense breaks by discovering that its favoured concepts, solid object, smooth distance, universal time, clear simultaneity are local conveniences rather than eternal truths, and theory breaks when it predicts singular behaviour and thereby points beyond itself. Still, one should not give the impression that everything dissolves into fog the moment conditions become extreme. Physics remains highly successful over enormous ranges. White dwarfs, neutron stars, gravitational lensing, black hole mergers, gravitational waves, all these can be described with extraordinary accuracy in the right frameworks. The breaking begins not in the sense of total ignorance, but in the sense that each framework has a boundary beyond which it can no longer claim final authority. This is what makes the edge so interesting. We know enough to identify it clearly. We do not yet know enough to step beyond it with confidence. And it is right there at that edge that the question of the early universe begins waiting. Because if forces can break matter, bend space, and embarrass common sense in collapsing stars and black holes, then one naturally wonders what sort of conditions must have existed when the entire observable universe was once compressed into a far smaller, hotter, denser state than anything we now see around us. That is where the story begins turning from local catastrophes to the first moments of everything we can observe. Once black holes have taught us that gravity can compress matter to the point where space-time itself becomes part of the event, it becomes almost impossible not to ask a larger question. If collapse in one corner of the universe can drive physics toward its limits, what about the beginning of the universe as a whole? What about those earliest moments when everything we can now observe was packed into a state far hotter, denser, and more extreme than any star, any neutron core, or any black hole environment we have directly described in ordinary language? If force can bend, break, and reorganize reality in local catastrophes, what was force doing when the entire visible cosmos was young enough to make every later structure look calm and mature by comparison? The Big Bang is one of the most famous phrases in science, and also one of the most misleading. It sounds like an explosion in space, as though the universe began as a compact fireball that burst outward into a pre-existing emptiness. That is a helpful image only for the first few steps, and then it begins causing trouble. The modern picture is subtler. The Big Bang was not matter flying into empty space from one central point. It was the early hot dense state of space-time itself, followed by expansion. Space was not the stage waiting outside the event. Space was part of what was changing. This matters because when we talk about force in the first moments after the Big Bang, we're not talking about a blast wave travelling through an otherwise stable environment. We're talking about the behaviour of a universe in which energy, density, temperature, geometry, and causality were all woven together under conditions of extraordinary intensity. As one looks backward in cosmic time, the universe becomes denser and hotter. Galaxies draw nearer in the mathematics. Radiation becomes more energetic. Matter and light become harder to distinguish in familiar terms. At some stage, atoms could not exist. Go earlier still, and atomic nuclei could not survive either. Earlier again, and even protons and neutrons are no longer durable units in the way they later become. The universe was not just smaller, it was less settled. The structures we now take for granted had not yet emerged. This is important because force in such a setting cannot be understood as acting on the kinds of objects we are used to discussing. There were no planets, no stars, no molecules, no crystal lattices waiting to fracture, no chairs for common sense to sit on. Force in the early universe belongs to a world before the furniture had been assembled. That alone should make us cautious. Many of the words we use in physics carry a great deal of baggage from the calm middle range of reality where we happen to live. We speak of particles, fields, motion, pressure, temperature, and time as though their meanings were obvious and universal. They are clear enough in their domains, but in the first moments after the Big Bang those domains overlap in severe ways. Gravity was not a background correction. Quantum effects were not minor details. Energy density was not a local oddity. The whole observable cosmos was immersed in conditions that brought the deepest ingredients of physics into close contact all at once. This is why the Planck scale enters the story so naturally here. If there is any era in cosmic history where Planck force and related Planck quantities deserve serious attention, it is the earliest one. The phrase Planck era is often used for the unimaginably brief interval at the beginning of cosmic history, where our present theories can no longer be trusted in their usual separate roles. Before that interval ends, or perhaps better said below that scale, we do not possess a complete and tested theory capable of describing the universe with confidence. General relativity becomes too classical on its own. Quantum theory without gravity becomes incomplete. We suspect that space-time itself may have been fluctuating in ways our current language cannot properly capture. If one asks what exactly happened then, the honest answer is not a dramatic narrative but a respectful pause. We know that our current map points toward a frontier. We do not yet know what lies beyond it with full clarity. Still, the frontier itself teaches a great deal. Planck force becomes relevant here not because we imagine some giant hand pushing the newborn universe outward, but because the scale of intensity in the earliest moments may have approached the regime where any meaningful upper force bound would matter. If today black holes signal what happens when gravity and concentration become extreme in local regions, then the earliest universe may have represented a global version of extremity. The whole observable region was compressed into a state where the difference between ordinary matter, radiation, fields, and geometry becomes more difficult to maintain. In that sense, the early universe is the place where the idea of maximum force stops sounding like a speculative aside and starts sounding like a structural question about cosmic beginnings. There is a temptation here to imagine the first moment as some kind of infinitely compressed singular point from which everything burst forth. Classical equations, when pushed backward, do encourage that language, at least in a simplified way. But most physicists treat such singular behaviour not as the final literal story, but as evidence that the theory has been extended beyond its proper jurisdiction. Much as a black hole singularity signals the likely failure of classical general relativity at the deepest level, the singular origin of the universe in classical cosmology signals the same sort of warning. The mathematics is pointing toward a boundary, not necessarily handing us the finished description of reality. This is why discussions of the first moments after the Big Bang quickly become discussions about what kind of theory replaces the old one there. That replacement would almost certainly need to say something about quantum gravity. And once quantum gravity enters, Planck scales are no longer decorative. They become the natural language of the problem. Planck length, Planck time, Planck energy, Planck force. These are not arbitrary units chosen for dramatic effect. They are the scales at which our current distinctions between the very large and the very small, between gravitational structure and quantum behaviour, begin to break down. So when we ask what force meant in the earliest universe, one possible answer is that it meant whatever our future theory of quantum gravity says it meant, but that the characteristic scale of the question was already pointing us toward Planck force. This leads to a delicate but interesting idea. Suppose there is indeed a maximum force in nature, or something very close to it, then the earliest universe might not have exceeded that bound in any meaningful sense, because the bound itself could be part of what shaped the way the universe emerged from its most compressed state. In other words, the limit would not merely be a ceiling imposed later on cosmic events. It might have been part of the architecture from the beginning. The universe would not begin in a way that violated its own deepest structural constraints. Instead, the earliest possible state would already reflect those constraints, perhaps through a geometry, a quantum bounce, a discrete structure, or some other mechanism not yet fully understood. That suggestion is attractive because it turns the question of maximum force into a question about cosmic order rather than cosmic excess. The early universe would not be a place where all rules were absent and everything happened at arbitrary intensity. It would be a place where the deepest rules mattered most. That is often the case in physics. Limits do not become less relevant at extreme conditions. They become more relevant. The speed of light matters most when things approach it. Quantum principles matter most where small-scale structure becomes unavoidable. Any maximum force principle would matter most where energy concentration and space-time curvature become severe. The first moments after the Big Bang are therefore exactly where one would expect such a principle to show its hand, even if only through the way our current theories signal their own incompleteness. There is another reason the early universe is helpful here. It reminds us that force is not always about opposition between already formed objects. In daily life, force appears as push against resistance. But in the young universe, what counts as an object, what counts as a field, and what counts as a stable region of space may not yet have been cleanly separated. The familiar cast of physics had not fully taken the stage. That means Planck force in the early cosmos is not best imagined as one thing pressing on another in a mechanical sense. It is better imagined as the natural intensity scale relevant to the dynamical structure of the whole young universe. It belongs to geometry, energy density expansion, and the conditions under which space-time itself may have been emerging into a smoother classical form. This also helps explain why inflation often enters nearby discussions, even if one must treat it carefully. Inflation is the idea that the early universe underwent a phase of extraordinarily rapid expansion, smoothing and stretching space-time in ways that help explain several observed features of the cosmos. Inflation, if correct in roughly its standard spirit, occurred after the deepest Planckian regime, or at least after the stage where the smooth, classical picture became more serviceable. But it remains relevant because it shows that the early universe was not simply a monotonic cooling of a featureless fireball. It may have passed through phases where fields dominated, expansion accelerated, and quantum fluctuations were stretched into the seeds of later large-scale structure. In that setting, the idea of force becomes even less like a shove and more like a property of how fields and geometry guide the evolution of the cosmos. One of the most fascinating possibilities is that the small irregularities that eventually became galaxies and clusters may have roots in quantum fluctuations from the early universe. If so, then the calm distribution of stars we see on the largest scales today owes something to tiny primordial variations generated when the universe was astonishingly young. That is a very gentle reminder that the extreme and the familiar are often more closely related than they first appear. The first moments after the Big Bang were not merely an inaccessible prelude, they helped shape everything that came later. The force scales relevant then may seem remote from our world, but their consequences are written into the structure of the cosmos we inhabit. Still, one must be honest about what remains unknown. We do not yet know whether space-time was discrete at the earliest times. We do not know whether the universe began from a singularity, a bounce from a previous contracting phase, a tunneling event, or something else that our current words barely hint at. We do not know whether maximum force is a strict universal principle, a suggestive feature of general relativity, or part of a deeper law not yet fully formulated. What we do know is that the early universe drives these questions together. It places force, gravity, quantum behavior, and cosmic origin into a single frame and asks them to make sense collectively. There is something almost elegant about that. The same force scale that appears when we ask about the ultimate intensity of gravitational influence also becomes relevant when we ask how the universe itself began its observable history. The limit of local compression in black holes and the beginning of global expansion in cosmology are not separate curiosities. They are two sides of the same deeper puzzle. One asks what happens when too much mass and energy fall inward. The other asks what was true when everything was once compressed far more severely than it is now. In both cases, the answer seems to lie beyond classical space-time alone, and that brings with it a subtle shift in how we should think about beginnings. People often imagine the beginning of the universe as a kind of first tick of the cosmic clock. But if time itself behaves differently near the Planck regime, that image may be too simple. The earliest meaningful after may only arise once a smoother notion of time emerges from a more primitive quantum gravitational state. In that case, The first moments after the Big Bang are not merely early moments on an already running clock. They may be the phase in which the very conditions for a classical clock became possible. That makes the question of force even more delicate. Force usually assumes motion and time. If time in the usual sense is emergent near the beginning, then force there may also need a more fundamental reinterpretation. Yet even this uncertainty is informative. It tells us that Planck force is not merely a giant number tacked onto the side of cosmology. It is a clue about the scale where the usual concepts of force, time, and geometry require revision. The early universe is where that clue becomes impossible to ignore. Our current theories can describe a great deal after the first fractions of a second with remarkable success. They can track nucleosynthesis, cosmic background radiation, structure formation, stellar evolution, and much else besides. But at the very beginning, where force and curvature may have reached their most meaningful natural limits, we still stand at the threshold. There is also a psychological comfort in this, oddly enough. People sometimes assume that the earliest universe must have been pure chaos, a wild, lawless explosion before order gradually emerged. Physics suggests almost the opposite. The early universe may have been more constrained by deep law than anything we now encounter. It was not casual disorder, it was severe order under extreme conditions, an order so deep that our present theories can only approximate its outer edges. If a maximum force principle exists, then the beginning of the universe would be one of the clearest places where that principle mattered, not as a dramatic prohibition, but as part of the grammar of reality from the start. And once you see that, another question naturally follows. If Planck force is relevant to black holes and to the first moments of cosmic history, does that mean there truly is a maximum force built into nature? Or are we only seeing a suggestive pattern produced by the limits of our current theories? The next step matters because it asks whether Planck force is simply a natural scale we should respect, or a real universal bound that nothing physical can surpass. That question has been waiting quietly in the background for some time now, and it is probably best not to rush it. Is there truly a maximum force in nature? Not just a practical limit, not just the point where steel bends or stars collapse, or our equations begin looking nervous, but a real universal bound built into the structure of reality itself, a deepest ceiling, a hard edge beyond which force does not merely become difficult or exotic, but impossible in principle. It is the sort of question that physics both loves and mistrusts. Loves because the history of science is full of discoveries that turned vague suspicions into clean laws. Mistrusts because the universe has a habit of punishing us whenever we mistake a suggestive pattern for a final truth. There is always the temptation to declare victory too early, especially when a number as elegant as Planck force appears and seems to whisper that nature has given us one of its hidden thresholds. But elegance, while often a good sign, is not the same thing as proof. So the honest path here is the more interesting one. We have to ask not only whether a maximum force sounds plausible, but what kind of evidence, reasoning, and physical meaning would justify believing it. Let us begin with the appeal of the idea itself. It feels right, in a certain deep and orderly way, that a universe with a maximum speed might also have a maximum force. We already know that relativity does not allow information or causal influence to travel arbitrarily fast. That limit is not an engineering inconvenience. It is structural. It shapes what counts as before and after, cause and effect here and there. So it is not outrageous to imagine that nature may also place a structural bound on how intensely momentum and energy can be transferred across space-time. A universe with built-in limits has a kind of internal dignity to it. It feels less like an unregulated contest of arbitrary magnitudes, and more like a place whose architecture matters at every level. And yet, force is not as straightforward a candidate for an upper bound as speed. Speed is a relatively clean concept in relativity. Different observers may disagree on many things, but the role of the speed of light as a universal causal limit survives the disagreement. Force is more slippery. It depends on how motion changes, over what time, in what frame, and by what description. Even in classical mechanics, force is tied to circumstance. In relativity and field theory, matters become still subtler. One can talk about stresses, energy fluxes, curvature, momentum transfer, pressure, or local field intensities in ways that overlap with but do not always reduce cleanly to a single universal picture of force. So if there is a maximum force, it has to be stated with care. Otherwise, one risks mistaking a suggestive phrase for a rigorous law. This is one reason the idea often appears not as a widely advertised theorem in every introductory textbook, but as a conjecture, a serious and intriguing proposal connected to general relativity and horizons. The central intuition is that if one tries to transmit too much force through a region, or concentrate too much energy too intensely, space-time does not remain passive. A horizon forms, causal structure changes, and the process is no longer visible or transmissible in the ordinary sense. In this picture, the bound is not enforced the way a speed bump slows a car. It is enforced by gravity reorganizing the situation so that the would-be excess is hidden behind an event horizon, or otherwise prevented from manifesting as an unconstrained visible transfer. There is something satisfying about this because it links the limit to a real physical mechanism rather than an abstract commandment. Nature would not be saying no because it dislikes large numbers. It would be saying that beyond a certain intensity, the geometry of space-time itself changes the category of the event. This makes the conjecture feel less arbitrary. It also ties it directly to black holes, which is exactly where our earlier discussion has been leading. Black holes are not mere curiosities here. They are the natural response of general relativity to excessive concentration. If a maximum force exists, one would expect horizons to be central to it. A useful way to think about the matter is to ask what would have to happen if there were no maximum force. Suppose just for a moment that force could be increased without bound in an unconstrained way. One might then imagine transferring arbitrarily large momentum across arbitrarily small regions, while space-time continued to behave as a calm stage beneath the action. But general relativity gives us reason to doubt that picture. Energy and momentum do not merely move through space-time, they help shape it. If enough is concentrated into too small a region, the geometry changes dramatically. At some point, the very process of trying to exceed the bound would trigger black hole formation or something close enough in spirit that the old description ceases to apply. In that sense, general relativity itself encourages the thought that unconstrained arbitrarily large force may be physically self-defeating. That is the strongest argument in favour of a true maximum force. It does not rely only on aesthetic preference or numerical elegance. It arises from the gravitational response of space-time to concentrated intensity. If you keep turning the dial upward, the world does not simply endure more of the same. It changes the setup. A horizon forms, visibility ends. Outward influence is no longer transmitted in the same way. This has the flavour of a bound not merely in practice, but in principle. Still, principle is a dangerous word in physics unless one knows exactly which theory is providing it. General relativity is extraordinarily successful, but it is not the final theory of everything. It does not include quantum gravity in a complete way. Near the Planck regime, where maximum force ideas become most suggestive, we already suspect that classical spacetime is not the whole story. So one might reasonably object that a force bound derived from the behaviour of horizons in classical or semi-classical gravity could be telling us something profound, but not necessarily something final. Perhaps the bound is exact. Perhaps it is approximate. Perhaps it emerges in one regime and is reinterpreted in a deeper theory. These are not trivial distinctions. There is also a conceptual issue about what exactly we mean by force in the relevant regimes. In familiar mechanics, force is tied to acceleration and momentum change. In general relativity, gravity is not strictly a force in the old sense, but a manifestation of space-time curvature. In field theory, one often speaks more naturally about stress energy. interaction terms, flux, or scattering amplitudes than about force as a single universal primitive. So the question is there truly a maximum force in nature? Partly depends on whether force is the most fundamental language in which to state the limit. It may be that what is deepest is not force itself, but a bound on tension, momentum flux, power, or information-carrying capacity, of which force is one practical face. This would not weaken the idea so much as refine it. Physics often improves by discovering that an initially intuitive statement was true in spirit but needed a better formal language. Temperature feels like heat, until we learn it is related to average energy distributions in statistical mechanics. Gravity feels like a pull, until we learn it is space-time curvature in general relativity. So maximum force may turn out to be one of those truths that is meaningful, but whose exact deepest statement is slightly different from the first phrase that made it memorable. There's also a reason some physicists remain cautious. In different coordinate systems, different frames, and different theoretical descriptions, local quantities can behave in ways that make universal force statements subtle. One wants a bound that is physically invariant or at least robustly meaningful, not one that depends on clever bookkeeping or on a poorly chosen notion of what counts as force in a curved space-time. This is why the best discussions of the topic tend not to trumpet it as settled dogma. They explore it seriously, connect it to horizons and black hole mechanics, and note that it fits beautifully with certain aspects of general relativity, while still allowing that the final status of the claim may depend on a deeper theory. That said, there are several reasons the conjecture remains compelling despite the caution. One is its simplicity, another is its connection to black hole horizons. Another still is that it mirrors the way physics often translates deep limits into geometric facts. The speed of light is not merely a speed limit painted on an invisible motorway. It is built into the structure of space-time intervals. In much the same way, a maximum force, if real, would not be a policy choice of the universe. It would be built into how geometry responds to energy concentration. This kind of structural limit is exactly the sort of thing modern physics has taught us to take seriously. There is also an intriguing relationship between maximum force and maximum power, the rate at which energy can be transmitted. If force concerns how strongly momentum can be transferred, power concerns how rapidly energy can flow. In relativistic settings, these ideas are closely related. Some versions of the conjecture are expressed more naturally in terms of a maximum possible power through space-time. Again, horizons play a central role. Excessive flux does not remain an unconstrained flux. Space-time reacts. This reinforces the larger theme that what is really being bounded may be not brute push in the ordinary sense, but the capacity of space-time to mediate influence without altering its own causal structure. And that is perhaps the most mature way to phrase the matter. A true maximum force in nature would mean that the universe does not permit arbitrarily intense momentum transfer through an otherwise open and visible space-time region. Push too hard, and the region ceases to remain open in the same way. That is a much richer statement than simply saying force cannot exceed a number. It says that the architecture of space-time and gravity sets a limit on how concentrated dynamical influence can become before geometry intervenes. Still, one should hear the objections too, because they keep the idea honest. Some physicists worry that maximum force is not fundamental enough to survive all theoretical reformulations. Others suspect it may be a feature of certain classical gravitational arguments rather than a universal principle of whatever the final theory turns out to be. Still, others would prefer to frame the deepest bounds in terms of entropy, information, area, or quantum constraints rather than force itself. These are not dismissals so much as warnings against overstatement. Physics has room for beautiful conjectures, but it insists that beauty earn its keep. There is also the possibility that maximum force is true in a certain restricted and powerful sense, but not in every naive formulation one could dream up. Science is full of statements that are both profound and domain-specific. Nothing travels faster than light is true in the sense that matters, but one can still speak carefully about recession of distant galaxies or phase velocities in ways that require nuance. In the same spirit, maximum force may be a deeply meaningful bound on physically realizable transmission across horizons or in open space-time, while still requiring care about what counts as the relevant force in a particular formalism. That kind of qualified truth is still very much truth. It is simply the kind physics usually offers. A question often lurking here is whether any observation could settle the matter decisively. That is difficult, because the bound concerns the most extreme conditions in the universe, where direct experiment is not exactly convenient. We can observe black holes, neutron star mergers, gravitational waves, and other violent phenomena. We can test general relativity with remarkable precision in many regimes. We can study high-energy processes and search for signatures of new physics, but a direct laboratory probe of Planckian force limits is beyond current reach by an absurd margin. So the case for a true maximum force must be built mostly from theory, consistency, and the structural lessons of relativity and gravity rather than from a tidy benchtop demonstration. And yet, this does not make the question idle. Theoretical physics often advances by discovering that certain principles bring wide regions of knowledge into alignment. Conservation laws did not begin as simple observations of every microscopic process. Symmetry principles were not obvious to ordinary intuition before they became foundational. If maximum force helps illuminate black holes, horizons, information flow, and the gravitational response to energy concentration, then it may be more than a curiosity even before it is elevated to the status of settled law. It may be one of those ideas that teaches us where to look, and what a deeper theory will probably have to respect or reinterpret. There is also something almost philosophical in the background. A universe with no upper limit to force might still be imaginable in the abstract, but one wonders what sort of world it would be. Would space-time remain coherent? Would causality remain intelligible? Would black holes, horizons, and the stability of large-scale structure look anything like they do? Our actual universe seems to prefer a more disciplined arrangement. It permits a great deal, but not without consequence. Energy concentration, gravitational collapse, and causal structure are all linked. That linkage is exactly what the maximum force idea tries to capture in a single bold sentence. So where does that leave us? Not with a tidy yes or no, but with something better. We can say that there is a strong and elegant case, rooted in general relativity and the behaviour of horizons, for treating force as having a natural upper scale and perhaps even a true universal bound of the right order. We can say that Planck force, or a closely related value, is the natural candidate for that bound. We can also say that the exact status of the claim remains bound up with deeper questions about quantum gravity, the nature of space-time, and the most fundamental language in which physical limits should be expressed. In other words, the idea is too serious to dismiss and too alive to call fully finished. That kind of answer may sound less satisfying than a clean verdict, but it is more faithful to the texture of real science. Physics is not merely a warehouse of final answers. It is a disciplined conversation with nature in which some ideas arrive as crisp laws and others as powerful clues waiting for their final form. Maximum force may be one of those clues. It may already be telling us that the universe has a ceiling on how intensely events can be arranged before geometry itself changes the terms. Or it may be pointing toward an even deeper principle in which force is only one visible aspect of a broader bound on action, information, and space-time structure. Either way, the question has done valuable work. It has taken us from ordinary pushes and pulls to black holes, to the early universe, to the edge of our theories, and to the suspicion that the world is not infinitely permissive even in its most violent moods. There may indeed be a final limit on force, but what is perhaps even more striking is what that possibility says about the character of reality. It suggests that the universe is not just a place where things happen, but a place where even the extremity of happening is shaped by hidden order, and once that possibility has been allowed into the room, one naturally begins to wonder what such a limit means not only for physics, but for our wider picture of the cosmos, its structure, and our own curious habit of seeking boundaries in a world that so often feels without end. By the time we arrive here, after following force from ordinary experience to stars, from stars to black holes, and from black holes to the first moments of the universe, the original question no longer sounds quite the way it did at the start. How strong can any force get seemed at first like the sort of thing one might ask out of simple curiosity, perhaps in the same spirit as asking how hot a fire can burn or how fast a machine can go. But the farther we followed it, the more it stopped being a question about large numbers and started becoming a question about the character of reality itself. If there is an ultimate limit, then that limit is not just another fact on a chart. It is a clue about what kind of universe this is. That, I think, is the quiet meaning worth sitting with for a moment. Physics often seems loud from the outside. Black holes, cosmic explosions, ultimate forces, the first instant of the universe. These are not small subjects. They are the sort of topics that attract dramatic voices, large graphics and music that sounds as though someone important is about to step out of a doorway in slow motion. But underneath all that, there is usually something more restrained. Physics is not really about noise, it is about structure. It is about finding out whether nature has shape where we once saw only events. A limit, if it is real, is one of the clearest signs of shape. There is a kind of comfort in that. We often live as though the world is made mostly of surfaces. A wall is hard, a glass is fragile, a road is straight enough. The sky is above us. Time passes. Objects move. These are perfectly serviceable facts for daily life. One can get through a very respectable number of years without wondering whether force has a maximum value, whether space is smooth all the way down, or whether black holes hide a deeper order behind their horizons. But once those questions are asked, something shifts. The world stops being a collection of familiar appearances and begins to look more like a system with hidden rules, a place where even the most violent possibilities may still be bounded by something deeper than themselves. That is striking because force has always had a slightly unruly reputation in the imagination. It sounds like the sort of thing that overwhelms. The stronger the force, the more it seems that limits should disappear, that one thing should simply impose itself on another with increasing authority. But the physics of the last century and more does not really support that rough picture. Again and again, it teaches that increasing intensity does not lead to endless freedom. It leads to thresholds. Push harder, and atoms stop being useful. Harder still, and nuclei stop being the right language. Harder still, and space-time itself begins to answer. Force does not grow without consequence. It grows until the rules begin changing in response. That is what makes an ultimate limit so interesting. It suggests that the universe is not built like an empty warehouse where events of any intensity may unfold as long as enough energy is available. It is built more like a structured environment in which very large intensities eventually call forth structural replies. Horizons form, geometries change. Distinctions we took for granted begin to fail. A maximum force, if it truly belongs to nature, would not be a prohibition added from outside. It would be part of the way the world holds itself together. There is another side to this that feels less cosmic and more human. We are creatures who look for edges. We ask for maximums and minimums partly because we want facts, but also because limits make the world feel intelligible. There is a fastest possible speed. There is a coldest meaningful temperature. There may be a smallest useful scale of time and length. And perhaps there is a greatest meaningful force. These ideas do not shrink the universe. In a curious way, they make it larger. A bounded world is not a lesser world. It is a world with architecture, and architecture is what allows complexity to exist. Rooms exist because walls are somewhere. Music exists because sound is not every sound at once. A sentence makes sense because words cannot mean everything simultaneously. limits are not always the enemy of richness. Very often they are the condition that makes richness possible. One can see that in the universe itself. If gravity behaved differently, stars might not shine in stable ways. If the basic scales of physics sat closer to ordinary life, matter might not remain calm long enough for chemistry to build anything interesting. If space-time permitted arbitrary intensities without structural response, perhaps black holes, causality, or the large-scale order of the cosmos would look very different indeed. The fact that we inhabit a region of the universe where planets can cool, oceans can gather, atoms can remain loyal to their arrangements, and nervous creatures can stay awake wondering about fundamental limits, all of that depends on the deeper rules being neither too loose nor too severe. That balance is easy to miss because daily life is so narrow compared with the full range of physical possibility. Most of us will never stand near a neutron star, and I think on balance that is for the best. We will not watch space-time warp around a black hole from a safe observational platform while sipping something warm and making careful notes. We will not directly witness the earliest moments of the universe, yet the hidden order of those remote conditions still matters here. It matters in the existence of stars, in the stability of matter, in the long history that made heavier elements, planets, and eventually living minds possible. The extreme and the ordinary are not separate worlds, they are linked by the same rules. This is perhaps one of the nicest things physics teaches when it is allowed to unfold slowly. The most remote questions often circle back to the nearest facts. Why is the universe stable enough to contain galaxies instead of only chaos? Why do stars last long enough for planets to cool? Why do atoms behave in orderly ways? Why does time seem to move in one direction? Why is there room in reality for both violence and long calm intervals? A question about ultimate force turns out to be tied, however indirectly, to all of these. Limits shape possibility. The ceiling matters because life unfolds far below it. And yet one should not turn this into a sermon about cosmic neatness. Physics is at its best when it remains honest about what it does not know. We do not yet possess a complete theory of quantum gravity. We do not know whether maximum force is a final universal law or a powerful clue pointing toward one. We do not know exactly what replaces the singular language of classical relativity in the deepest regimes. We do not know whether space-time is fundamental or emergent, smooth or discrete in some deeper sense, or something that our current words only clumsily approximate. What we do know is already enough to make the question serious. Nature gives every sign that it resists arbitrary concentration through gravity, curvature, and horizons. Whether that resistance is best stated as a strict maximum force or as part of a deeper principle remains open. But perhaps openness is part of the quiet meaning too. Not every profound scientific idea arrives fully finished. Some enter as strong hints, as places where the theories line up just enough to suggest hidden order, without yet revealing the whole mechanism. That does not make them weak. Sometimes it makes them more valuable. A finished answer can be filed away. A good, unfinished answer keeps working on the mind. It keeps connecting things. Planck force does that. It links force to gravity, gravity to black holes to horizons, horizons to the structure of causality, and all of that to the earliest universe. Whether it is the exact final ceiling or the signpost toward a deeper statement, it has already earned its keep. There is something else worth noticing. The limits uncovered by physics are rarely limits of imagination. They are limits of process. Nothing prevents us from picturing greater and greater pushes in the abstract. The mind is very good at adding more and more to a sentence. Bigger than that, stronger than that, hotter than that. But reality is under no obligation to honour every extrapolation of language. At some point the world pushes back, not in anger, but in structure. That is one of the most useful correctives science offers to intuition. It teaches that some questions cannot be answered by simply extending familiar pictures forever. There comes a point where the picture itself is what must change. We have seen that several times in this journey. Falling apples led to universal gravity. Universal gravity led to stars. Stars led to collapse. Collapse led to black holes. Black holes led to the suspicion that too much concentration changes the geometry of reality. From there, the idea of maximum force began to look less like a dramatic guess and more like a possible summary of how nature preserves coherence under extreme conditions. It is almost modest when phrased that way. The world remains itself because even its fiercest events are not free of order. I think that matters beyond physics, though one has to say that carefully. It is easy to become sentimental about science and start using it as a mirror for whatever feeling one brought into the room. Better to stay grounded. What physics really gives us is not moral advice, but perspective. It shows us that the universe is not chaotic in the lazy sense. It is subtle. It permits both stability and change. It allows stars to burn calmly for ages and also permits black holes to form. It allows gentle tides and violent mergers. It allows long, quiet histories and brief catastrophic events. And underneath all that, it may still be governed by limits that prevent intensity from becoming meaningless. That does not tell us how to live, but it may tell us something about what sort of place we live in. A place with boundaries is not necessarily a prison. Often it is what allows patterns to persist. A river has banks, a melody has timing, a conversation has turns, at least in the best cases. Likewise, reality seems to have banks and thresholds of its own. The speed of a light is one, the quantum scale is another. Perhaps Planck force is yet another. Each one says in its own way that the world is not made of arbitrary freedom but of constrained possibility. And constrained possibility is not a disappointing idea. It is the reason complex things can exist at all. By now, the question, how strong can any force get, feels less like a challenge and more like an invitation to see the world differently. The strongest force is not simply the last rung on a ladder of stronger and stronger shoves. It may be the point where force ceases to be merely something happening inside spacetime and becomes something that calls forth spacetime as a participant. That is a profound shift. It means that ultimate limits do not sit at the edge of the world like warning signs. They are woven into the world from the beginning. That returns us in a very gentle way to the first moments after the Big Bang. If the deepest scales matter anywhere, they mattered there. If there is a maximum force, it was not an afterthought. It would have been part of the grammar of cosmic birth itself. The same may be true in black hole interiors or at the edges of horizons. In that sense, ultimate limits are not merely the things that stop us. They are the things that define the terms on which reality unfolds. They are not obstacles added later. They are part of what gives the universe its identity. And perhaps that is why the subject feels oddly calm once one has spent enough time with it. At the beginning, ultimate force sounds severe, almost aggressive. By the end, it sounds more like a statement about balance. Not balance in the sentimental sense, but balance in the physical sense. The universe allows extraordinary intensity, but not without answer. It allows compression, but not without geometry. It allows extremes, but not without structure. That is not a dramatic conclusion. It is a quiet one. The world is deeper than it first appears, and its deepest truths may be limits that hold even when everything else is being pushed to the edge. So here we are, a little farther along than when we began, having asked how strong any force can get, and discovered that the question reaches into almost everything. Matter, gravity, stars, black holes, the early universe, and the nature of space-time itself. Not bad for a word as ordinary as force. It has a way of hiding its ambitions until you start following them carefully. And now, before we part from this particular topic, I find myself wondering again where you are listening from, and what sort of hour it is there now. Perhaps it is later than when we started. Perhaps the room is quieter. Perhaps the ideas have settled a little, or perhaps they are still gently turning over in your mind. That is all right. Physics is often most enjoyable when it does not rush to leave. It lingers in the background and makes ordinary things feel slightly more connected than they did before. If you found any comfort in this slow walk to the edge of force, if the subject kept you company, or if it simply gave your thoughts somewhere interesting to rest for a while, I would be very grateful if you liked the video and subscribed. It helps this quiet corner of science reach other people who enjoy taking the long way around a difficult idea. For now, though, it is enough to let the question rest. Somewhere between the push of a hand, the weight of a star, and the hidden order of space-time, nature seems to keep its own counsel. It allows much, but perhaps not everything. And in that restraint there is a kind of clarity. The universe may be vast, but it is not shapeless. Even at its most extreme, it may still be held together by limits so deep that we notice them only when we ask the largest questions we know how to ask. Sleep well, wherever you are, and whenever this finds you.